In this series, we will be discussing many of the core items that are required to understand and program Scala effectively. So let's begin with what is Scala. Scala is billed as a multi-paradigm language. What that means is that it's a language that takes two vastly different identities in programming languages and merges them: object-oriented programming and functional programming. Scala's design began in 2001 with the first release in 2003. Programming languages often take time to mature and become saturated in the mindshare of the community. Around 2008 is when Scala's interest started gaining traction. The language is supported by a large and growing community with varying backgrounds and disciplines. Today, Scala is one of the most well-known and respected alternative languages on the Java virtual machine. In this session, we discuss the positives of Scala. Scala's strengths you'll find, not only in this series, but as you progress, are many. For one, Scala has type inferencing, so that you don't need to declare everything explicitly. And although you don't type much, it is also statically typed, where you know the type associated with every reference. Scala is also a language that offers other features, like functions, pattern matching, clean syntax and API, currying, partial functions, partially applied functions, implicits, operator overloading, infix operators, and more, and some of which we'll find in this particular video series. Now, as someone who has knowledge of currently 10 different languages, I find Scala very complete without much aggravation. It'll be tough to reach what I call the ceiling with this language. And what I mean by the ceiling is the point where things become either weird, obscure, or awkward for the programmer. Although every language has its strengths and weaknesses, it'll be very tough to find that ceiling in the Scala programming language. It wouldn't be fair to the viewer if I didn't cover the negatives of Scala. First off, let's start with one of the obvious. Scala is difficult. It is an extremely powerful tool, and because of such, there are many that find this language hard to understand and to use it. The analogy I use is moving cinder blocks up to the top of the building. In order to move that cinder block, you could either do the simple thing, take those blocks, put them on your shoulder, and start walking up the stairs, or you can put the investment of learning how to use a crane. With a crane, though, you will have to learn the mechanics, wind, tension, safety, and weight capacity. The rewards for accumulating that knowledge are immense. Another issue is that Scala currently suffers from a soft skill issue, and that is finding talent. There are many jobs, and often there are not many that could fill it. If you are interested in either creating or migrating a project to Scala, it is worth investigating your team options before proceeding. And although I find this more of a positive than a negative, is that while language engineers do care about backwards compatibility, they will not hold up the next release of the language over it. In other words, Scala, again, cares about backwards compatibility, but not that much. It isn't going to be like Java. So what effect does this have on the community and how they work with Scala projects? Well, let's take a look at a very popular Scala-based library called ACA. And what I'm going to do is I'm going to go over to search.maven.org on the browser. And let's take a look at some of those dependencies. Okay, so here we are. Now, if you want to use actors within Scala, you'll notice something like this, where I have ACA actor 2.10, all the while I have a version like 2.3.14. And over here I have ACA actor 2.11. Now the 2.10 and the 2.11 are Scala versions. And these versions over here are the versions for the library itself. So you have this divergence. One is they have to maintain the version of Scala. And for every library, so this one has a 2.11 version and a 2.10 version, but that library itself has versions of its own. So this is a side effect that you would have to be aware of. Now again, is this truly a negative? I do not think so personally, but it would be something that you should be aware of before engaging in the Scala programming language. In this session, we discuss where to download the Scala programming language. Before we talk about downloading, Scala is a JVM-based language, so a Java is required. In particular, a JDK, or Java Development Kit. And this is required before proceeding, And because the Java Development Kit has the compiler, all that is needed. As of Scala 2.11.7, JDK 6, 7, or 8 is required. JDK 8.0 is preferred, and not only that, as of April 2015, JDK 8 is the only version supported by Oracle. To download the latest JDK, you could either use your search engine to look for Java download or JDK download, or you can go to this website, oracle.com/technetwork/java.se/download/index.html. This is what the page looks like. I'm going to scroll down a bit, and here I'll find the JDK download button. I'm going to click on the JDK download button, and this takes me to the download page. Choose your flavor and architecture and install per the directions. I'll be running my examples on Linux. Next, we must download Scala, and this can be found at scala-lang.org. Let's see what that looks like. Here's the scala-lang.org website. And here, I will click on the download link. Now, here's the page for the Scala download, and we'll select the button that states Scala 2.11.7. For Mac OS X and Linux, this will be a TGZ file, or a tar.gz file, and it'll be up to you to expand the file in whatever location you desire on your home directory. Please make note of the location, since we'll need that later when we set up our environment variables. Windows users, this will download an executable .msi file. Once that is downloaded, double-click the .msi file. Now, as a note, for Linux and Mac users, there are package installers that you can use, if you so desire to. What we've just described is adequate enough, but if you want to use the package manager instead, then you can do so. For Mac OS X, you have a magnificent installer called Brew. And to install Brew, just follow the directions at brew.sh. This is a website. Once Brew is installed, you can install Brew with a command called brew install Scala. For Linux, particularly those with a Debian flavor, you can use apt-get or apt-cache to see if Scala is available. So here's apt-cache. So use apt-cache to look to see if Scala is available. And here's the command sudo apt-cache search Scala. Once you found it, you can use sudo apt-get install and Scala. So in conclusion, you need a JDK from Oracle and prefer that you use version 8. If you're viewing this recording much into the future and there's a version 9, then use the latest one. Remember, use the JDK, not the JRE. JDK has the compiler. JRE is just a runtime for the end user. For Linux and Mac OS X, this would be a tar.gz file. For Windows, this will be an MSI. You can double-click on that .msi file. And if you'd like, you can use package managers installed on your machine, and this is only applicable for Mac OS X and Linux. In this session, we're going to make sure that Java and Scala are mapped correctly in our environment variables. So our goal in this session is to make sure that all of this works in a terminal or command prompt. Java C space dash version, Java space dash version, Scala C space dash version, and Scala space dash version. We're going to start things off in the Windows operating system. Here I am in Windows, and I'm going to open up the command line by hitting the Windows key and typing in CMD. And I'm going to open up the regular command prompt that comes with Windows. If you have a specialized command prompt, open that. Now, let us try our set of goals. Java C space dash version, that didn't work. Java space dash version, that one did. Now that worked because the Windows installation by default will always make this runtime Java executable work. It won't make Java C, which is the compiler, work. So we need to do a little bit of work in order to get that working. So Scala C space dash version is the other goal that we were looking for. That did not work, and I'm going to assume that neither does this one. So we need to go to the environment variables and set up Java home and Scala home. I'm going to hit the Windows key and type env. So you can see I have two entries here on the right-hand side. Edit the system environment variables and edit the variables for my account. Now, the edit environment variables for your account might be your only choice since many users are on work machines and they don't have the full access to their machines. I'm going to select Edit the System Environment Variables. I have complete control of my machine. And what I'm going to do here is once I have this box open, I'm going to click on Environment Variables. Now I have user variables for my account up here. That's the first box. And I have system variables down below. Now down here, what I'm going to do is I'm going to create an entry. And this entry is going to be called Java_home, all in caps with an underscore. This is a standard name. And what this is going to do is it's going to point to a location of my Java install. So what I'm going to do is I'm going to go down over here and load up the Explorer and look for the location of my Java install. Now, if you went ahead and accepted all the defaults when you installed Java, this in all likelihood is going to be inside of Program Files and Java. So I have JDK180_25. I'm going to go ahead and highlight that. Now what I'm going to do is I'm going to click on this box right up here that shows the file structure. And I'm going to just use my mouse and click on that, and now I get to see there's the complete path. I'm going to copy that, and I'm going to go over here to the system variable, and I'm going to paste that location in here. All right, so we've established the Java home. Now inside of my system variables, I'm going to include Scala home. And now let's go to the Explorer and find out where this is located. Now, if you downloaded the MSI, which is in all likelihood that's what you did, this will be located in somewhere around C program files x86/Scala, but let's verify that first. So we're going to be looking for C/program files x86, and somewhere within here we're going to look for Scala, and here's Scala right in here. And here are all the folders that we're concerned with. So I'm going to copy this location, and I'm going to paste that onto here. So variable value in here will be C program files x86/Scala. I'm going to go ahead and click OK. And next is the path. Now, as you can see here under user variables, I have a path here. I also have a path here for the system. I have access to the system, so I'm going to edit this one. So I'm going to highlight path and click on edit. Now, once I'm in here, now there are some entries that are already available, and I don't want to mess around with what has already been established. So what I'm going to do is I'm going to merely append or add Java_home, \bin, make sure it's a backslash and not a /, another semicolon, %Scala_home, %\bin. And here I'll click OK. Now, let me open up the path just so that way you can get a quick review again of what this looks like. So again, this is semicolon, %Java_home, %\bin, semicolon, %Scala_home, %\bin. Now I'm going to click OK all the way out of these settings. OK, OK, and OK. I could even close this Explorer now. And I am going to close out of the command prompt because any settings that I have made for my environment variables will not take hold for any command prompts that are already open. Therefore, I'm going to close it and I'm going to open up a new one. Now let's review our goals. Java C --version. Great. Java --version. Great. Scala C --version. Great. And finally, Scala --version. Fantastic. All 4 passed. Everything looks good, and we are ready to use Scala in Windows. Here we are in Mac OS X. This is a standard install where Bash is the default shell. I already installed the JDK DMG, and Java works just fine. In fact, what's great about the Mac installation is that Java C and Java already work. So let's take that for a spin. I'm going to hit Command Space and locate terminal. Well, I already had that there. Here's terminal. And let me go ahead and maximize this. And let me increase the font. I'm going to do a Command plus to increase the font a bit. That should be a good size for us. And I'm going to try out the following. Java C --version. There it is. And Java -version. This should be automatic for us. But what doesn't work is Scala. Now, I downloaded a tar file from scalalang.org, and I already expanded it, and here it is. It's right over here, Scala 2.11.7, so that works pretty good. What I'm going to do, let me hit a Control-L just to start off with a clean screen, is that once I downloaded this, by default, this will not show up. This will say command not found. And if I do a Scala space dash version, this will also say command not found. Now, if I install this using brew, like I mentioned in the previous session, everything should be good to go and all your goals should be met. But if you're not seeing the Scala C space dash version or Scala space dash version working, then we'll need to create either a .bash underscore profile or a .bash RC. In this example, we'll be using a .bash underscore profile and we'll add some entries. So let me get started with that. So what I'm going to do is I'm going to use my favorite editor, Vi. You could use Emacs, you could use whatever type of editor is your favorite. And I am going to create a file called .bash underscore profile and edit that file. And here we are. I'm going to add the following entries. I'm going to export Scala underscore home. And again, please use your favorite editor here. It doesn't have to be the same one I'm using. And I'm going to put the location of where I expanded my tar file. And it just happens to be under /user/Dano, which is my name, /Scala-211.7. For the next line, I'm going to add export path. And I'm going to set that equal to $path. Now that path is going to retrieve the path that has already been established on your operating system and bring this in. And what I'd like to do is bring the already established path and append to it, and I'm going to use a colon in this case, $Scala underscore home /bin, B-I-N. That is it. Now what I'm going to do is I'm going to save and close this file. And now on my terminal, I'm going to type the following for the changes to take effect. Now let's try our 4 commands in our shell to ensure that we are ready. Of course, Java C-version works. Java-version should work as well. And now Scala C-version, that works out great. And Scala-version, and that'll work out great as well. We are ready to go. Now, I wouldn't call what I just did a full-on recommendation. Every shell has a set of files meant for different reasons. It could very well be that .bash RC is your preferred file. All this depends on your machine, how it was set up, how it is administered. Look up any documentation for your OS and your shell. Usually there are 2 different documentations. Discuss it with your system administrator as to the best place where to store your environment variables on Mac OS X. If you're the master of your own machine, .bash underscore profile, just as we've shown here, ought to work just fine. For the duration of the video series, I'll be using Linux. For Linux users, it'll be nearly the same setup as the Mac. So what I'm going to do is I'm going to open up a terminal, and here it is already, and see where I am with my 4 commands, what my goal is. Java C space-version, that works. Java space-version, that works. Scala C space-version, that does not work, and Scala space-version, that does not work. So I have 2 out of 4. Now, for the Linux users, the Java C or the Java may not work. On my particular machine, it is already mapped to Java C and Java using something called Update Alternatives. Check it out, it's a really great way to set up Java and you're able to choose which version you want. Now, for my example, while it is working well, I'll still have to map Java home in order for everything to work correctly. And as you can see, my Scala C space-version and my Scala space-version does not work, so we'll need to fix that. On my Linux machine, I'm using Z shell. So what I'll need to edit is my .zshrc file to add my environment variables. Now, you could use whatever shell you want. The most popular shell that is in use, of course, is Bash, followed by, I believe, Z shell. And either one of those are going to have their own particular files that you need to edit to set up the environment variable. So if you're using Bash, edit your .bash underscore profile or your .bash RC. If you're using ZSH, I'm going to be editing my ZSHRC. Now, I just told you the names of 2 popular shells that you can use with Linux. There are a lot more. Now, I'm going to open up my ZSHRC, and here it is. And in this file, I'm going to add my Java underscore home with the location of the version of Java that I wish to use. And I'm also going to create a Scala underscore home with the location of where my preferred Scala will be located. And then I'm going to take the location of all those and add them to my path. So here's a ZSHRC. It already has some information that ZSH needs, and I'm going to add the following. First off, I'm going to add the Java home, which is user lib JVM. Now, this is going to be different for everyone. This just happens to be the location on my machine. It could just very well be that this will be in your home directory, and you can add whatever path your JDK is located onto this line. So export Java home, and then the location of your JDK. Add a few lines here. I'm also going to add export, and I'm going to include my Scala home. This will be located under home, Dano, Java, and Scala 2.11.7. And then finally, I'm going to export a path. And very much like we did with the Mac, I'm going to set this equal to the path that is already established, $, $Java_home, /bin. That's different than Windows. Make sure it's a /, $Scala_home /bin. Now I will save the file, and now I will go to my terminal. I'm going to hit Control L, and I'm going to run source with that file, ZSHRC. That way all those changes will take effect. You could either type source.zshrc if you're using ZSHRC. If you are using bash, then you would type in source.bash_profile. I just happen to be using a different shell for this example. The other alternative is to close out the terminal and open up a brand new one. So let's go through our goals. Control L, Java C-version. Okay, we already knew that one worked. At least it did on my machine. Java-version. Scala C-version. Fantastic. And then finally, Scala-version. And if it all works, we're good to go. And we showed you how this is set up in Windows, Mac OS X, and Linux. So in conclusion, edit the environment variables per your operating system. Make sure your Java home and Scala home are established, and ensure that the following works: Java C --version, Java --version, Scala C --version, and Scala --version. In this section, we're going to talk about how to create a script in Scala. For many Java programmers out there, you may not be quite as familiar with scripting, although you may have played with a little bit of scripting in other programming languages. But in Scala, there's no need for a compilation or a public static void main string args. Although Scala programmers tend to compile their code just to make it fast, there is no requirement to do so. So what we're going to be doing in this section is we're going to be creating a file, a script, again without a public static void main string args and without compilation. For this, you'll just need an editor. There are plenty of great ones out there. There's Sublime, which has Scala syntax highlighting. There are some other editors that don't have syntax highlighting, but they're great nonetheless, like Notepad++, TextPad, UltraEdit, Visual Studio Code. For those who enjoy the classics, there's always Vim and Emacs, and there's plenty of syntax highlighting for Scala for both of those editors. If you want to edit code with any IDE, there are some great ones out there. There's Eclipse, and you can download Eclipse with a plugin called Scala IDE, which you can get at scalaide.org. Or you could go to scalaide.org and download an actual full-blown IDE with all the plugins readily available. There's also IntelliJ. Once you download IntelliJ, go to the plugins, and you can download the Scala plugin from there and edit files. There's NetBeans, which also has a Scala plugin. And if you want to stay with Visual Studio, then you can use Visual Studio, but there won't be any syntax highlighting for Scala. What I'm going to do is I'm going to start off with a script. And I have a folder here called Creating Script Scala, delimited by underscores. And what I'm going to do is use touch to create a script called intro script.scala. Once there, I'm going to bring this up in my editor. Just so you know, there's no touch in Windows, so if you want to create this in the Windows operating system, then you can just go ahead and fire up an editor and create the file from there. Once I have this available, I'm going to hop over to my editor, Alt-Tab. Now, once I'm here in my editor, what I'm going to do is I'm going to go ahead and open up that file that I just recently created, and I'm going to get started with something very simple. I'm going to do a print line for all the Java programmers coming in. There's no system.out.println. We just head straight towards it and do a print line. I'm going to do an open paren and a quote and stay here that Scala is amazingly concise. Close the quote, close the paren, and we're good to go. For Java programmers, you'll notice something is missing, the semicolon. No need for a semicolon in Scala. I save the file, and we're good to go. I'm going to Alt-Tab over to the terminal. Once I'm here in the terminal now, I can just type in Scala, intro script Scala. Again, there's no compilation involved with this. It is going to be interpreted, it is going to run quickly, and we'll get a Scala is amazingly concise. That's how easy it is. Again, no compilation involved. Now, what if I want to create a shell script that I could run on Mac OS X or on Linux? Let's go and get started with that. I'm going to create a script called intro script.sh. Not a Scala extension, but a .sh extension. Now, I'm going to head to my editor. Here in my editor, I'm going to edit the file called intro script.sh. And for the first line, I'm going to include a hash and a bang. And I'm going to specify that I want to use sh for the shell script. The next line, I'm going to specify that for this particular script, I wish to execute Scala. This funny argument that I'm going to type here specifies the name of the file. And this next funny argument that I have here is going to be for all of the arguments for this particular script. I'm going to close things up with bang and hash. Once I'm done with this 3-line prefix, I'm going to go about this using just plain Scala. So I'm going to do a print line, and again, specify that Scala is amazingly concise. Close the quote, close the paren, and I'm going to save the file. And that's all there is to it. With that 3-line header, that's enough information to provide for our shell script to run as a script. So let me head over to the terminal. Now that I'm here, there's one adjustment I need to make. I need to make sure that this particular file that I just wrote is executable. So I'm going to chmod +x, which turns the flag on to make it executable, introscript.sh. Now I can just run this just like any other shell script. And as we see here, it specifies that Scala is amazingly concise. That's how easy it is. It's a fast setup, and once you become familiar with the language, this might be your preferred scripting language for days to come. In this section, we're going to talk about how to create an app in Scala. The previous section, we created a script, which was interpreted. Now we're going to be creating and compiling source code, which then becomes JVM bytecode, which then we can use to run or make it a part of a library. Now for this section, we're going to need an editor. And what I'm going to do here in the terminal is I'm going to start off by creating a file called myapp.scala. Now I'm going to bring this up inside of an editor. Alt-Tab. Inside the editor, let me bring up creating app Scala, which is the folder where I'm placing this Scala file. I'm going to bring up myapp.scala. So inside of this file, I'm going to start off with a very basic class. I'm going to call this class employee. There's no need for public. Everything is public by default. And I'm going to start with an open paren, and I'm going to start adding the properties. First property I'm going to add is first name, followed by a colon, then the type. If you're coming in from Java, this is reverse of what you expect. In Java, you expect to do a type first, then the name of the property or variable name. Inside of Scala, we'll do the property name first, colon, then the type. Now I'm going to add last name followed by the type. At the very basic level, this is not all we need, but it's sufficient. So I'm going to save this file. Now, if you're coming in from Java, you're going to notice something a little bit alarming. The class name is called employee, but the file name is called myapp.scala. The Scala compiler is going to allow this. Scala compiler is going to do a lot of things for you that you don't have to particularly think about all that much. In fact, you could even create multiple classes within the same file. Let me show you an example. Let's say I want to create a class called department, and a department has a property called name with the type string. In fact, I could also make it a part of this employee class. So now this employee has 3 properties, first name, last name, and department. I have 2 classes within one file. Pretty amazing. I'm going to go ahead and save the file, and now I'm going to switch over back to the terminal. So back at the terminal, I have one file. Let's take a look. There it is, myapp.scala. Now what I'd like to do is I'd like to compile this file, and I'm going to do so with Scala C, which stands for Scala Compiler. and I'm going to specify the Scala file that I wish to compile. Now that I'm done, let's take a look at what is inside my folder. Now I created two classes inside of my app.scala. And when I compile it, what it's going to do is it's going to create two Java class files. Now if I want to take a look at the class files, I can use Java P. And Java P will allow me to introspect these class files to see what's contained in it. I'm going to use Java P space -p. -p allows me to view a lot of private information within this particular class file. And I'm going to specify employee. And when I do so, I could take a look at the internals of the employee class that I created. This is Java, and this says that I have a class called employee, and I have a constructor called employee with 3 arguments. First one's a string, which represents the first name. Second one's the last name, which is a string. And then finally, a department. Again, this is all JVM bytecode. Now let's say I wanted to get organized. What I'd like to do is I'd like to remove the class files from here. They could always be regenerated using the compiler. And here's my app.scala. What I'd like to do, let's say I want to create a source folder and I want to create a classes folder where all the compiled classes will be placed. Let me do a tree to show you what that looks like. Now, tree is freely available for Mac OS X and Linux. For Windows, there's also a tree. The only thing that you would have to do is make sure that you specify that you want to see files as well. But this is available to all Windows users. So what I'd like to do is move my app.scala into the source folder. I'll go ahead and do that right now and do a tree to see where we're at. So I have my app.scala inside of the source folder, and I have a classes folder to compile to. Now, if I want to compile my app.scala, I can use the Scala compiler. And I'm going to use a switch called D, which will allow me to specify where the class files will be sent to. I'm going to specify that this should go into the folder called classes. And now I'm going to state that for the source files, I want you to look inside of the source folder and look at any Scala file within it. Now let's take a look at the tree. All the class files are inside of the class folder, and the source files still stay within the source folder. And that's using the Scala compiler. Now I have to warn you, this myapp.scala is for compiler use only. If you're going to compile it, you cannot run it as a script. Let me show you an example of that. I'm going to go back to my editor. This says right down here that the file is no longer available, which is true. So let me go ahead and bring this up. This is now under the source directory under myapp.scala. Make sure we're editing the right one. But let's say I want to treat this like a script. Again, warning, this will not work. Because I have 2 classes here, that's fine, I can compile that. But the print line right here is now going to be treated as a script. Now, I can run this as a script, but I cannot compile it. Let me show you what that looks like. I'm going to bring up the previous command that I had before. Again, my app is inside of the source folder, and inside of the classes is where everything is going to be compiled. If I'm going to compile a Scala file which is modeled as a script, I will get this expected class or object definition. It doesn't know what to do with that print line. I can run it as a script, and there's nothing wrong with doing that. I just can't compile it. So you'll have to know the difference. And this sums up how to create an app inside of Scala. So you could either choose compilation or you could choose interpretation. But when you choose compilation, be sure you compile code that is not a script. To recap, source code can be compiled or can be interpreted. If you are going to compile, use Scala C. If you're merely going to interpret it as a script, then just run Scala on that file. In this section, we're going to talk about val and var. And in order to do so, I'm going to head over to the REPL. And here on the REPL, what I'm going to do is I'm going to declare val a is equal to 100. I am declaring what's called a value, and a value is not reassignable. This is analogous to final in the Java programming language. Let me show you what happens if you try to do a reassignment. You'll get a reassignment to val. Now, opposite of this is a variable. It's a variable because it varies. You can change the contents. So if I have var b is equal to 400, I can reassign that at any time. I cannot, however, change the type. This is a static type programming language, So once it's already been established that B is of type int, I cannot make it a string. Scala programmers will prefer the use of val over var, and var are used in things like actors and other controlled environments, like in a single method where there's only one thread and it's being used to create an object. A lot of projects you'll need to reflect why it is you're using a var and having a fairly good reason as to why you want to use it. Let's show another example. Let's say I have val a is equal to 400 once again, and we'll see here something else happened. This says that this is of type int, but did I declare so? No. What happened here is that Scala inferred the type for us. We could be explicit if we want to by stating that a is of type int and then specify the integer, but the type inference does a fairly good job of knowing what type this is before declaring it. Now, if I wanted to change the type, let's say instead of val a of type int, I wanted to make it a double, it will then make the appropriate actions to make sure that the type for a is of type double, and in fact the content now is changed to 400.0, which is of type double. It is not an integer. It is a floating point. That is one way to change the type. Now both of these are declaring types explicitly. The val a colon double is not only declaring a type explicitly, but it's also coercing that 400, which is of a type integer, and coercing that into a type double. We could also do a coercion if I specify something like val a is equal to 400 colon double. This is essentially after the fact. What's happening here is we are creating an integer of 400, then we're placing in the colon double, which in turn is going to coerce this into a double. And when this double is assigned to a, therefore the type inferencer is going to make sure that a is of type double. Two different ways to go about this. Let's show another example for type inferencing. Let's say that I have val a is equal to 100, and let's say I'm going to declare val b is equal to hello. The type inferencer is going to see b as of type string. Now what I'd like to do is declare another value called c, and what I'm going to do is I'm going to take b, I'm going to add a string with a comma to it, and I'm going to add a. Now the type inferencer is going to figure all this out, and therefore the type system is going to declare in an inferred way that c is of type string. Now types are needed to satisfy the type systems, and at times you will need to add your own type just to make sure that the type system gets it right. It does a pretty good job at inferring the type you want, but sometimes it will make mistakes, and you'll have to explicitly state what type it is that you're meaning to do. So in conclusion, vals are not reassignable, but vars are reassignable. But vars are rarely used, and we usually have to think about why it is we're using a var and what's the reason for it. Types on both val and var are implied. You will be given types by the type system, called inferred typing. But in case it gets it wrong or it doesn't understand your intent, types can always be explicitly defined in your declarations. In this session, we discussed lazy val. A lazy val is just like a val we just covered, with the exception that a lazy val will not be evaluated until it is called. Let's try the following as an example in the REPL. Here we are in the REPL, and what I'd like to do is just try out a lazy val. Here I have lazy val a is going to be the name of the value, and I have a block. And a block is just multiple statements. Let me correct this. First statement is I'm going to print line evaluated. The second statement is 5, and that 5 will inevitably be assigned to a. Now I'm going to hit enter. As we see right here, a is right now assigned to lazy, or this bracket lazy. In other words, a is not being assigned to anything as of this point. Now once we make a reference to it, then it will be evaluated. So if I hit a right now and hit enter, we will get the print line of evaluated, and then finally a will be assigned to 5. And if I do this again, we will no longer get the print line evaluated, but we will see that it is 5 because 5 is now fixed to a. It only takes one invocation, and thereafter every subsequent call will have that assignment made again and again. Every call just shows the evaluated result the first time we referenced a. Now, there is no such thing as a lazy var, only lazy vals. Now, one thing that it is possible is with lazy val is the ability to forward reference a val, particularly without a warning. So let's give this a try in a script called lazyvals.scala. So here I am inside of lazyvals.scala, and I'm going to add 3 lines. Val A is equal to 10 plus B, but B is not established yet as of line 1. Then on line 2, I have val B is equal to 19. And finally, we'll print line in A. So I went ahead and saved this file already. And I'm going to run the script, and what we will see is a warning. Our warning will state reference to uninitialized value B. Scala was able to kind of wire things together. It was, after all, a simple script. Sometimes it will be a warning, sometimes it will not. But as it's stated right here, at of this moment, B has not been initialized. Now, if we retrofit those assignments with lazy, we could find that these warnings will go away and we can make that code snippet work. So let's head back to our code. There we go. I've added lazy in front of those vals. Now, if we run the script, warnings go away, and we prove that this is particularly useful for wiring components together. And if we're stuck with a component that comes first dilemma, lazyval gives us that power to defer that until it is needed. Now let's talk about another fascinating side effect when it comes to lazy vals, and that is when exceptions occur. So we'll turn to our REPL this time for our next example. Here I'll have a divisor, and here I'll have a lazy val with a quotient. And this quotient will be 40 divided by that particular divisor. As you can see here, quotient is lazy. Now if I print line that quotient is being referenced. We get, of course, division by 0, arithmetic exception. But since the first invocation failed, Scala is forgiving and gives you an attempt to do it again correctly. And if successful, it will then lock the val quotient to that value. So if I change divisor to 2 and finally do a print line quotient once again, we will get 20. So in conclusion, lazy vals do not evaluate until it is called upon. Any subsequent calls will return the already established result. There is no such thing as lazy var. Also, lazy val is forgiven if an exception happens the first or second time, or third or fourth. Until it is able to make the assignment, that's when it will lock. In this section, we'll be discussing how to bend values and variables to our will. Scala offers several tricks that allows us to be expressive in a flexible way. There is a concept called internal DSL where you can make a host language have a look and feel of another language. As you increase your knowledge in Scala, you'll be introduced to other libraries and tools that will make Scala look like an entirely different language. This section presents some of those neat little tricks. We start off on the REPL with the following. I'm going to start off with a val, and then I'm going to start off with a backtick. This is the key that's usually right next to the 1 and above the tab. And I'm going to enter in my greatest gift in dollars. I'm going to close things off with a backtick. And I'm going to assign that to 500. As you can see, I've created a value with spaces in between words. For those with Java experience, this is welcoming since there are no spaces in any of the variables in the Java programming language. Now, before we go on to the next example, we need to learn what an opchar is. In the Scala specification, Scala has a definition for an opchar. Opchar is any Unicode character from U0020 to U007F. For more information on these Unicode characters, visit unicode.org/chart/pdf/u0000.pdf. Now for the next opchar, we have Unicode symbol math. These are mathematical symbols that we can place in a variable or a value. And for a list of these mathematical symbols, go to the following link. Finally, you can use Unicode symbol other. These are other symbols that you can place within a value or variable. And for more information, visit this following link. And what can we do with some of these strange characters? Well, let's go back to the REPL. In a val or var, you can put any opchar after you establish an underscore. Let's try it out. I'm going to create a val called Is This My Salary Per Year? Underscore. And this time I'm going to use a question mark. May seem strange, but this allows us to be flexible. Now, if I want to reference it, let's try this out. Let's say this should be my raise, underscore with an exclamation point. Now I'm going to reference the previous value that I've just created, and I'm going to add 50,000. I just gave myself a raise. Now let's go back to backticks. Backticks can also be used to create a value or variable that are reserved keywords in either the Scala or Java programming languages. As you can see here, import is a reserved word for Java, and it just so happens to be a reserved word in Scala. If you wish to reference keywords in backticks, be careful. For example, this will not work. It doesn't work because import is a keyword, and the parser will first recognize that as something that it should import. You will have to make sure that any subsequent reference also has the backtick. So in order to do this correctly, I need to include the backtick. If you decided to make a value or variable with a backtick and it surrounds a non-reserved keyword, let's say for example magic, this is not a reserved keyword in either Java or Scala, then I can safely reference that value or variable without the backticks. Of course, don't go nuts. You still have to work with your coworkers, and for our next example, we're just going to do something silly. But you'll get the point how flexible the Scala programming language can be. Let's try that we want to include a val void and set that equal to 100. I'm also going to create another val called false and set this to true. And I'm also going to set return and set that equal to 90. What do you think the answer is going to be for this statement? If false, which is true, then return void, which is actually 100. Otherwise, return return, which is actually 90. Again, a silly example, I wouldn't recommend this for production code. So in conclusion, val or var have spaces and other valid identifier characters, including opchars, if surrounded by a backtick. They may be referenced without a backtick if they are not reserved. Otherwise, you'll need to include backticks. Any val or var without a backtick can include a valid Scala identifier known as an opchar if followed by an underscore. In this section, we're going to talk about primitives, byte short, int long, float, double, character, and Booleans. Now, I think for the most part, many programmers already know the basics of these items. So I'm going to run down fairly quickly with this, but also I'm going to do this with a twist. Of course, that twist is we're using a different programming language. So let's go to the REPL and play around. Let's start off by creating a byte. I'm going to do so by creating a val b and specifying that the type here is of a type byte. A byte is an 8-bit number, which is the same as it is in Java. The maximum formula as defined in Java is the same as it is in Scala. 2 to the n minus 1 minus 1. Therefore, the maximum number you can have as far as a byte is concerned is 127. If you go much larger than that, you'll end up with either a type mismatch or what's called an overflow. In specifying a type, I could either do so at the value declaration, or I could coerce it after the number. Now a short is 16 bits. Therefore the maximum is 2 to the 15th minus 1 minus 1, or 32,767. And the minimum is negative 2 to the 15th. And if we go just one more over the bounds, we'll end up with a type mismatch. Again, I could also do this, specifying the type after the number. Now, integers are the default in Scala. I don't have to specify an int. I can specify the type, just like anything else, next to the value, or I could specify the type after the number. Oftentimes, that is unnecessary. Now, longs are 64-bit and either require the type definition or the type after the number using coercion. Here it is using coercion. If you don't want to use either one of those, you could specify an L at the end of the number. This is using Java's style. You could also use a small l, but I don't recommend that because that looks too much like a 1, and depending on your font, that could get easily confusing. Floats and doubles are IEEE 754 standards, same as it is in Java, and floats can be explicitly stated by type. But this can get kind of tricky. Let's specify a float value, and what we're going to do is add the suffix f. Therefore, it's going to be listed as a float or a capital F. If I specify the type here as a float, but forget the f, this will be listed as a type mismatch because it's going to assume to be a double. So what I have to do is make sure that I add an f. If I add the coercion without the f, that is still considered a type mismatch. So again, I need to make sure that I either have the small f or the capital F. Now, doubles, on the other hand, are the default when dealing with decimal points. Without specifying a D, without specifying a type of double, this is going to be understood to be a double, is going to be type inferred to be a double. I can add types wherever I need to, either by coercion or by adding it to the value. I could also explicitly add a d to the end of that number or a small d. Doubles have more precision than its float counterparts. Doubles are 64-bit and floats are 32-bit. Now let's talk about characters. Characters are very much like in Java, where when you have to specify a character, you put single tick marks around it. Now if you wish to specify a Unicode character, you can do so with a single tick mark, \u, and then enter the Unicode value of what you're trying to represent. This will be a theta. Now Booleans are the same basic construct as it is in Java. We have true and we have false. They do not correspond to ones or zeros. They are values onto their own. Now last thing to mention is that unlike Java, Scala's primitives may be treated like objects. Now, I'm careful when mentioning that they may be treated like objects. When calling an operation that works perfectly fine as primitives, Scala will not box or wrap the primitives up in another object. Only when calling a method that requires an object will an object be created. Best thing about Scala is that you don't have to concern yourself how or when this wrapping occurs, since a compiler will typically do that for you. Now consider the following statement. 1 plus 4. Obviously it's going to return 5. Now when you're actually running this, what's happening is you're actually adding two primitives together. And while that in itself is not exciting, knowing that you could also express that addition as a method on an object will allow developers to maintain an object-oriented frame of mind. In other words, this operation looks just like an add, which is a method on an object with a parameter 4. So let's say I have 1, and let's say I just want to treat it like an object, and I'm going to call the method plus. There is operator overloading in Scala. And I'm going to call plus, and I'm going to give it the parameter of 4. Now these two end up with the same values. Again, in Scala, we can treat everything like an object. That doesn't mean everything will be an object when it comes to compile time or runtime, just only that we can treat it as an object. Now, there are times in Scala where there are actually objects being wrapped up in order to add certain functionality. Let's take the following as an example. This looks very clean. I have -5.abs, and abs is a method on int that calculates the absolute value of this int. Now this requires a little bit of history knowledge when it comes to Java. Now for those coming in from Java, you know that in order to get the absolute value, you have to bring up this annoying little method called math.abs, math being the class and abs being the static method, as you give it the value you're trying to calculate the absolute value for. Scala has cleaned most of this up. I'd rather do -5.abs rather than math.abs. For one reason, if you're using an IDE, you can have code completion give you all the necessary functions you need pertaining to an int without having to look up some kind of static method in some other class. Now in Scala, it looks like abs is an inherited part of int. And it's doing so through a trick called an implicit wrapper. And notice how the abs function here just seems like it's a natural method for that number. In this case, there's an adapter, a class that wraps around an int called richInt. And it provides nice little methods like abs, among others. Every primitive type in Scala has a corresponding wrapper. For car, there is richCar. For Boolean, there's richBoolean. For long, there is richLong, and so on. Scala will convert any primitive into an object on an as-needed basis automatically, which is good. Scala will always work to our benefit, and we could just go on thinking in a functional and an object-oriented way. So in conclusion, all primitives work just like in Java with varying differences. Primitive assignments can be inferred by the type system, or you can add types manually as you see fit. Primitives may be wrapped by a rich wrapper depending on which method is called, and this gives a primitive more methods and more functionality than it originally had with Java. In this section, we'll be showing if, else if, and else in Scala, and some of the differences to expect when working in a functional programming language. For the most part, I think we understand to this day and age that if, else if, and else statements are fairly predominant. We know what they are, and given the knowledge of previous programming languages, we would expect someone new to Scala to know how to write if statements with some minor differences. So let's get started with a file called old if statements, and let's mock up something that a programmer first coming to Scala would write. Here's our file, oldifstatements.scala. Let's get started. My first two lines, val a is equal to 10 and var result is equal to an empty string. So we have if a is less than 10, then the result will be less than 10. Else if a is greater than 10, then it'll be greater than 10. Otherwise, we will state that it is 10. Therefore, less than 10 if a is indeed less than 10. Result will be greater than 10 if a is greater than 10. And if nothing else is valid, then we'll assign that to it is 10. All right, so we'll go ahead and save that. And let's go ahead and print out the result and see what we are looking at. Again, this is all under a file called oldifstatements.scala. Let's go and run it. Great, it says it is 10. Let's go back. And here we had that a is equal to 10, and the result is going to have the ending string of the result, which is assigned with each subsequent if statement. Now, if we didn't want to, we could just go ahead and get rid of some of these brackets here. For it to be a little bit cleaner, let's go ahead and save that and run it. There we go. This still says that this is still 10. Now these lines of code work just fine in Scala, but it is imperative. So let's go back. And that means that all computations are done in a series of statements. There is also this var right here under line 2. And as we mentioned in the video section about val and var, we like to avoid vars. The solution to this is to change this code into a functional style. So I'm going to rewrite this in a file called new if statements, and that way we can contrast the differences. So here's our file new if statements. Let's begin. Now this time the result is going to be assigned to the if statement. Perfect. Now let's print the result. Now that is a little bit different. Compare this to this. We don't have a var, so this is from our old file. We don't have a var, and we can essentially inline everything. And here's how it looks under new if statements. Now this idea may be a little bit new, but soon you'll become somewhat natural in your daily Scala development to do this sort of thing. Again, we can assign an if statement to a value, and in this case, the value is the result. Because we can do that, we can get rid of all the assignments to the result, since the end result of all this will inevitably be assigned. Now let's go ahead and run this. Let's go back to our new if statements. And I'd argue that this is cleaner, easier to read and understand, and avoids any kind of mutable reassignments. In other words, vars. So in conclusion, if statements exist just like in any other programming language. They can be used in an imperative fashion, or they can be assignable to a val in a more functional fashion. In this section, we'll be showing while loops and discuss its use and the migration to a functional style of programming. While loops are nearly the same as they are in Java and many other programming languages. It will run the code within a block as long as the condition for the while loop is met. So let's give this a try in a file called whileloops.scala. Okay, here we are at whileloops.scala. Let's get started. Here I set up var a is equal to 100 and var result is equal to an empty string. Keep in mind I am using a var, something that is able to change and not a val. We continue. Okay, we're done. So while a is greater than 0, we will continue along with this loop. We will set result equal to the number, or we will append that number to the result. If a is greater than 1, we'll add a comma to that. And afterwards, we will deduct 1 after each iteration of the loop. So let's see if this works. This should be somewhat very familiar to many programmers. Let's go over to the command line. And there we go, 100, 99, 98. all the way down to 0. So let's go back to our code. Now, this is not only imperative code, but has mutability with the A and the result. Remember, I mentioned we are starting off with var for A and result. Not to mention, this is also a lot of work. The same result can be achieved through more functional means. To give you a taste of functionally putting a comma after each number from 100 to 1, let's try something different. I'm going to start off with a file called functionalloops.scala. Okay, here we are inside of functionalloops.scala. And there we are. This will create a range from 1 to 100. We will take that range, reverse it, and we'll call a method called makeString, which will put a comma after each element within that range. Let's run it. Great, it's the same thing. Let's go back to our code. Again, this is a range from 1 to 100, reverses it, and creates a string delimited by commas. We could have also rewritten this by doing the following. This is now a range from 100 to 1 with each step decreasing by -1, then creating a string where everything will be delimited by a comma. Since the result is so lightweight as opposed to the full-featured while loop, we could also do the following. Now let's run it. Great. Let's go back to our code. Now this requires a retraining of our minds to think functionally. We essentially have to usurp years of imperative programming knowledge to do it. And maybe usurp is too strong of a word, since we don't want you to intentionally forget things. We want you to build upon your years of imperative programming knowledge, but the rewards in efficiency, readability, and maintainability in functional programming will be revealing over time. So the verdict of while loops, not used that often. There's usually some sort of programming that you can do functionally in place of the imperative programming. And there may be situations where you have no choice or intentionally require a while loop, but its use in Scala is going to be limited. And that goes for its crazy cousin, the do-while loop. So let's refresh our memory with a do-while loop. I'm going to create a file called do-while-loops.scala. Here we are in the file do-while-loops.scala, and we're essentially going to write the imperative programming example we did at the beginning of this session, but this time with a do-while loop. Now let's add a print line. Okay, same thing. This is a do-while loop. While a is greater than 0, we are going to append to it. If a is greater than 1, we'll add a comma to it. That way we can delineate between all the different numbers. And again, the do-while loop, for those I forgot, same as the while loop, except it will always go through at least one iteration. And if the variable a was 0 in this example, it would at least just print out the first number. But let's give this a try. Works out very well. But now, let's change things around. Because this is a do-while loop, let's say we changed a to 0. Now let's run it again. As we can see here, we get a 0 because a is established as 0. Let's go back. A is established as 0, and our while loop has a greater than 0. But a is not greater than 0. So therefore, our do-while loop is going to iterate at least once. So in conclusion, while do-while exists, just like any other programming language, but it's rarely used in Scala. While in do-while may cause the programmer to resort to variables and mutable state, and there will always be a functional equivalent for a while or a do-while loop. In this session, we'll be showing for loops in Scala and contrast them with for comprehensions. For loops are going to be interesting. For loops are also underused in Scala. And to be clear, I did say for loops. In other words, the way we knew for loops will be underused. We'll be migrating for the most part to a concept called for comprehensions. And that is an idea that is consistently used. But first, let's start off with a review of a for loop. And we start off inside of a file called forloops.scala. Here we are inside of forloops.scala. And we're going to get started with a result, and we're going to this time count from 1 to 100, and we're going to print the result with a comma between each number. This is very much like our while do-while example, but this time using a for loop. And that way we can become reacquainted to what a for loop looks like. Let's get started. And here's our for loop. It should kind of look similar. From 1 to 100, for each iteration, we're going to assign that to A. And within the block inside of the for loop, we can use that A however we would like to. Great. So for 1 to 100, we are going to assign each iteration to A, and we will append it to the string. And during this time, if A is less than 100, then we will go ahead and make sure that there is a comma. Now at the end of all this, let's go ahead and print out the result. Let's go ahead and run it. There we go, 1, 2, 3, 4, 5, all the way up to 100 with a comma between each number. Let's go back to the code. Now this is a typical for loop, the way you've known it for many years. And just like the while and do while, in order to use it, you typically have to have some sort of mutable variable, typically, but not always. And you have to have that set up in order to use it. Now this code example, again, is much like the while and do while examples we've had before. Now again, this is an imperative style. What we're going to be looking at in this session is more of a functional style as well. Now we mentioned for comprehensions already, and since Pandora's box is already opened, we might as well serve it to you up as an appetizer. But first, let's go about this the long imperative way. So we've seen this example, and this is just a typical for loop example. But now let's do something where we want to do some sort of computation for every item within a list, and we want to create a resultant list based on that computation. And we're going to start off with a file called forloops2.scala. Let's begin. Okay, and here we are inside of a new file called forloops2.scala, and we begin. Now in Scala, this is a list of 1, 2, 3, and 4. This is a list of int. And what I want is, I want to create a list of int, which will be the result. And what do I want in result? I want every element inside of XS to be added by 1 and placed inside of this new result list. Now, what is this bracket here? We'll talk about this in another session when it comes to collections, but this right here is a parameterized type or a generic type. This just says this is a list of int. And because this list is empty, I have to declare that this is a list of int. I could have done the same thing over here, but we have something called type inference, so I don't actually need this here. And again, for more information, we have a few sessions for collections and how all this works. Okay, but there it is. So we have a list of 1, 2, 3, 4. I have a resultant collection that is going to hold the same elements as XS, but we're going to add 1 to each element. Now, let's create the for loop. Now, this may be a little bit mysterious here, so let me stop right here. This is actually just a method on a list. And this is just a way that we could append an item to a list. And that's all that means. There is something called operator overloading, and we have more on that topic a little later. And what we're going to append to this result? Well, we're going to append whatever A is, but we're going to add 1 to it. Now, we'll print out the result. Now, let's run it. Great. List 2, 3, 4, 5. That is the list of 1, 2, 3, 4, but we're adding 1 to each individual element. Not so bad. Again, we took each element, added 1 to it, created a new list. We got what we wanted. Of course, the pain point is that var. Let's go back. So here's that var once again. Remember, we don't like that var, and we want to try to avoid it. Again, it's worth reiterating. Sometimes there's no way around it, but we like to keep this as a val if we can do so. So let's try this again in a functional way using a for comprehension. And this time I'm going to create a file called functional for loops. Okay, here we are inside of functional for loops, and we're going to do nearly the same setup. Now, we are setting the result to the for comprehension. This should look kind of similar to that functional if statement we had a couple of sessions ago, where we take the result and apply it to a value. The only difference now is we're also going to be using a keyword called yield. And yield will essentially yield a new collection that will be created, and the value is calculated. And in this case, this would be a plus 1. But let's see what it looks like first, and then we'll describe it. Now, this right here is what I was talking about, where it looks very similar to if. Now, if you remember a couple of sessions ago, we had the if statement But what was really weird about doing it functionally is that we can take that if statement and assign it to a val. Well, this time we could take a for loop, or what we seem to think is a for loop, it's actually a for comprehension, and assign that to a value. And remember, it says val result. It does not say var result. And now I'm going to call yield. Yield, again, just means that for every item that we get, I want to add 1 to it and yield it back to a new collection. And now we will print the result. Okay, that looks great. Now let's run it. We're going to run functional for loops.scala. It looks the same, doesn't it? Let's go back to our code. We see that this created a new list. And if we wanted to, we could do, just to verify that we have actually a new collection out of this. So let's save this and let's go to run it. First one is the new result. The second one was the original XS that we created. So let's go back. Now it's all just like the previous example, except this part is now in one glorious one line, and without mutability in the form of a var and imperativeness. We could just make that assignment directly. So there's more to what's going on. We'll revisit this topic when we discuss maps and flat maps. For now, just notice that the result is also a list. Now again, the XS stays the same, and by default, every operation in Scala will return a different collection from the original, since the original collection is likely immutable. And in this case, that list 1, 2, 3, 4 is an immutable collection. I did say likely because there are ways to work with mutable data structures in Scala. But for now, we're just focusing on the immutable data structure. So it is important to stress again also that with a for comprehension, the collection type that we get from yielding will typically be the same type as the collection we first started with. And in this case, it is a list. Result here is of a type list, and to be more precise, a list of int. So in conclusion, for loops are available in Scala, and you can use them just like you've used for loops in other programming languages. Now, the traditional for loops are actually underused in Scala. Scala programmers, the more advanced they get with the language, will start using for comprehensions more in favor than the traditional for loops. In this section, we'll be talking about strings. Strings retain the same basic structure from Java lang string. So let's start with a REPL. We get started with a very simple declaration. Val is equal to Scala. As you can see here, the string is surrounded by quotation marks. If you want to specify a type, you can, of course. You can always place it in the beginning, or you can always place that at the end. But this is usually unnecessary since the type has already been inferred. Strings are not primitives like numbers, Boolean, and characters. For Java programmers, they contain nearly all the same methods as you'd expect from Java lang string, but with more functionality. All the methods that are available in other collections in Scala are in Scala's string, since a string is merely a collection of characters. Strings can also have escape characters like tab, new line, carriage return, and a Unicode value. Let's try one. I'm going to create a string called escapes. Here's a tab, here's a new line, here's a carriage return, and finally here is a Unicode. That should be a lambda. So we have our tab, we have our new line, we have a carriage return somewhere in here, and we have a lambda. This has been a very trivial section on strings. In the next section, we'll show different types of strings called a smart string. In conclusion, strings are objects. They are surrounded by double quotes, and they have the basic functionality of other collections. Strings can also contain your escape characters like tab, new line, carriage return, and any kind of Unicode escape. In this section, we'll be discussing Scala's smart strings. Smart strings are a wonderful string construct that makes development a pleasure to work with in the Scala programming language, mostly because it gives us things like multi-lines and saying regular expressions. So let's start off with a file called Smart String Scala, where we'll create a multi-line string in the old classical way. So let's jump over to our editor. Now let's get started here, and we'll get started with some lyrics. So let's create some lyrics. Let's break out the Louis Armstrong. So let's start off here with I see trees of green, red roses too. I see them bloom for me and you. And I think to myself, what a wonderful world. All right, let's go ahead and save this as smartstrings.scala. And let's finally do a print line on this. And we should be good to go. All right, so there is our multi-line. This is the old classic Java way of creating a line each. We have to put carriage returns on this. We have to add plus at the end of each line. It can get kind of messy. So let's run this at the command line and smartstrings.scala, and looks fantastic. The only problem is it doesn't look quite as fantastic on the Scala source code itself. There are a lot of quotes. Again, there are a lot of new lines. So let's clean this up using a smart string. Now with smart strings, the only toll you have to pay is that you need triple quotes at the end of the line. But you can get rid of these quotation marks, and you could also get rid of, so let's do a quick search here, of all the new lines with the quote and the plus. There we go. So we have I see trees of green, red roses too. Let's make this a little bit more inline. What I'm using here is a visual block. There is something similar in IntelliJ and Eclipse. It's called insert mode. Take a look at your documentation and do something like this. It really makes programming a lot easier. Okay, there's our smart string. A little bit cleaner. Let's run it. Now as we see with the result, I see trees of green is flush to the left border, but we have some space before the red roses too and all the other subsequent lines. So let's go back to the code. We have an issue, and the issue is that Scala is merely doing what we told it to. And we have this large block of line, and all Scala is doing is interpreting these blank lines and putting them at the command line whenever we run our code. So my attempt to make my code look nice in the editor caused it to look different on the command line. Instead of cutting all this space out, leaving my code ugly on the editor, let's tell the smart string where the margins truly begin, and let's add a method to the end of smart string called strip margin. Let me use that column mode again, just because it makes things a little easier. I'm going to put a pipe in front of all this, and at the end, I'm going to call strip margin. Strip margin will use that pipe, or the OR symbol, as the default indicator of margin. Let's go ahead and run this. Great, everything is now flushed to the left-hand side. Now I could enjoy beautiful code in both my editor and my command line. Now what if I wanted to try a different delimiter for the margin instead of the pipe or the OR symbol? Strip margin will accept any character that you give it. Let's say we wanted to replace all of these with an @ sign, and what we can do is add that character as a parameter to strip margin. Let's run this. Good stuff. Let's go back to the source code and take a good look at it. So instead of a pipe again, I am using the @ sign. All I have to do is just specify as a method parameter to strip margin that I wish to use the @ sign. There's an additional bonus when using smart string, and that has to do with regular expressions. So let's do up a regular expression. I'm going to create a message, and the message will be, we are meeting on June 13th of this year and having lunch at 12:30 p.m. Now what I'd like to do is I'd like to create a regular expression. And what I want to do is I want to pluck out of this string the 12:30 p.m., the time. So we start off with something optional. So let's say that any space or 0 through 9 for the hour. The hour might be optional in case it's like 1 o'clock or 2 o'clock. That's optional. And we have 0 through 9. Of course, we need a colon. And now for the minutes, that could be 0 through 5 for the first number, and let's say 0 through 9 for the second. We'll need a space, perhaps 0 or more spaces, followed by whether it's AM or PM. So there's our regular expression to extract the time from this string. To make a regular expression out of a string, we are only going to call a method called R, which stands for regular expression. The problem with this, though, and the problem with a lot of strings in Java, is we have these double backslashes. And by nature, within a Java string, if we want to create a backslash, we have to do 2 of them. With smart strings, let's go ahead and convert this over to a smart string. We can get rid of the extra backslashes. We can now just focus on the pure regular expression without any extra annoyances. If you're curious about how to use this as a regular expression, let's print out the match. So we're calling this regex find all in within this particular message. And let's convert it to a list. You need the list, that way everything is displayed out in a nice way. Find all in will take that regex and find all instances within a particular string. When we run this, you'll see here at the bottom line, this says list 12:30 p.m. There was only one instance of a time within this sentence. With Scala, we can focus on what we want, and we don't have to tiptoe through a bunch of different rules like the double backslash escape in regular expressions. Smart strings gives us multi-line functionality without breaking up this string and putting a bunch of new line characters. Smart strings also gives us the ability to add margins into our code with a method called strip margin. Strip margin uses a pipe or an OR operator, if you want to call it that, by default. Strip margin also uses another character if we wish. We just need to provide that with strip margin. Smart strings are absolutely amazing for things like regular expressions by making it easier to escape characters. In this section, we're going to talk about string formatting. Scala provides a quick and easy means to do C style or Java style formatting of a string, much in the way that you expect in string format in Java, but with a few changes. Let's go in an editor and try out some of these changes. First off, I'm going to start off the classic way using string format. Let's go over to the editor. Let's create a string, and we're using the Java style string.format using a static method call. And we are going to state that this is a %s, and afterwards we are going to state that %s will need to be replaced by the string test. Let's print it out, and let's save this in a file called stringformats.scala. So we have val str, which is equal to the static method call. This comes from Java lang string. There's a static method call called format, which brings in a string. We have that %s, and that %s is going to be replaced by test. We'll print line the string and see what happens. As we can see, this prints out just fine. This says this is a test. Problem is, let's go back to the source code. The problem is that this is a static method call. And what would have been preferred is that we just call a method from a string. A string is already an object, and it would have been nice and very clean to call it up that way. That's what Scala gives us. So let's take this string and create a different one, but instead of using the Java style for it, let's go ahead and use Scala's style. This time I'm going to create a string called this is a %s. %s is what's inevitably going to be replaced, and we're going to call format with test. And let's save this, keep this here for a bit so we can take a look at it. Again, we have a string. This is a %s dot format, and test is going to be the argument which will be replacing the %s. We saved it. Let's go to the command line. They're the same thing, just a little cleaner on the second one using Scala's style. If you're new to string formatting, Java and Scala formatting variables can be found at this address. docs.oracle.com, Java SE 8. We are in Java 8 currently. Docs API Java util formatter.html. Let's take a look at an example of what is at this website. We will see that there are different characters representing different types that can be replaced in a formatted string. We used small s for it, but you could also have B for Boolean, C for characters, D for decimal integers, O for octal integers, X for hexadecimal integers, F for floating point numbers. We could have N for line separators. We could also use date and time conversions, say for example H for the hour of the day, I for the hour of a 12-hour clock, Z for time zones, Q for milliseconds, and on and on. There's capital B for the full month name, small b for the abbreviation of the month, capital Y for year. And you could also have different flags to change the way things are formatted. So go to this website for a reference. And what I'd like to do is use that reference in our code. Let's go back to our editor. Now let's try a Commodore's Classic. Actually, I'm not sure if it's Commodore's or just Lionel Richie, but it goes because you're once, it's generally you're once, twice, 3 times a lady. Now let's say we want to use format here. Now what goes on here, some of the Java programmers will call this var args or variable arguments. We in Scala call it repeated parameters, but the notion is the same, that within this format we can have as many number of parameters as we would like. So the first %s, let's say we'll do this in reverse, 3, twice, and once. This is already in a print line. Now compare that with the previous example we had, where we had only one parameter. Format accepts variable parameters, so if we want to use 1, that's fine. If we want to use 3, that's fine. If we want to use 10, that's fine. It will allow any number of parameters. Let's run this. Now it does it the order that it's specified. If we just leave it as %s, it's always going to choose the first one by default for the first %s, second one for the second %s, and the third one for the third %s. But if you cannot change the order, we can change the string format. Let's give that a try. I'm going to head back over to the editor. Let's say the third one needs to be the first one. So what I'm going to do is specify here, after the % that we want the third argument and we want to make that a string. For the second %s, we want to make that the second argument, but we still want to maintain that as a string. And then finally, for the third one, we want the first argument and still maintain that as a string. Again, the %3 states that we are going to get the third argument, which happens to be once. The %2 states we want the second argument, which is twice. And finally, the %1 here represents the first argument, which is 3. Let's run it. Works in the format that we need. Let's get a little fancier. This time I'd like to use Java Time. If you're not familiar with Java Time, it used to be called a library called Jota Time. If you're using a project that is JDK 7 or less, I highly recommend that library. The creators of Jota Time were brought over to Oracle, and they created a fantastic package that is now a part of Java 8 called Java Time. And I'd like to use Java Time in our next example. Let's go back to our editor. So what I'd like to do is I'd like to import the package. Again, it's worth re-emphasizing that this Java Time underscore that I'm bringing in, by the way, this underscore means bring me everything within Java Time. But again, this is with Java 8, and what's really great about this is that it is immutable, very much like everything by default is in Scala. We embrace immutability. So let's create a print line on this and say, we will be eating lunch. And in our example, let's say I want to bring in one date item, and it's going to be called local date. There are 4 different ways to create dates using the Java Time API. One is called local date, one is called local time, one is called local date, local time, and the other one is called zoned date and time. Local date is just the date with no reference to time zone. Local time is the time with no reference to a time zone or reference to a date. Local date time is the date and time but no reference to a time zone. And then zone date and time is everything. The date, the time, and the time zone. So let's say in this case here, I want to say, we will be eating lunch on, and let's say for this example, we only have one argument, but we need to use it 3 different times. So %1, and we need to specify that this is a time element, and B is going to be the month. So we'll be eating lunch on month. The day will be, let's say we want to use %1, this is a time, and if you take a look at the reference at the website, this would be the date, E. In the year, and now we want to specify the year. We still want to use the first argument. It is a time element, and here is the year. So B is the month. If I said that was year, that was incorrect. This is the month, this is the day, and this is the year. Finally, we will format the whole thing and provide it with local date. Local date now says, just give me the calendar of whatever it is on my system clock. Let's run it. We'll see here it says, we will be eating lunch on August the 12th in the year 2015. This just happens to be the date this recording was made. Let's go back to the code. Here it is. There is only one argument. That's why we have %1 here, we have %1 here, and we have a %1 here. All of these are time formats, which is why we have a T under all of them. Capital B is the month, E is the day, and capital Y is the year. It is worth noting, though, that all of this could also have been rewritten using printf. And instead of the format, we just need to include the variable. Let's go and run this. Now, as a well-rounded discussion, in our previous session, we talked about smart strings. So let me bring up the item we had with smart strings. And we had these lyrics from Louis Armstrong. And let's go back to our current file. And what I'd like to do is bring those lyrics in here, and here they are. By the way, in the previous session, I had misused this word. That should have said of. But let's say given this string, what I'd like to do is everything that is a color, I'd like to do a variable replacement of that. So I'm going to do a %s here. And of course, for the green, which is also a color, do a %s. So if I want to do substitution everywhere where I have a %s, I could also do this on a smart string. So I'm going to call format with green and red. Let's print out these lyrics. And let's take a look at the end result. Now everything's caught up here to the top, just because we needed to do a new line at the end of the previous one. But we get the idea here. I see trees of green, red roses too, and so on. Let's go back to our source code and do a review. So we have string format. This is the Java way. This is the older Java style. Under the this is a %.format, this is Scala's style. This format, we are using positions because your %3 would be the third argument, %2 the second, %1 the first argument. In our fourth example, we used time to do formatting. We used the first argument over and over because we wanted to separate the month, the day, and the year. And in our final example, we used a smart string from our previous session. And this time we replaced all the colors with %s. So if we want to change the colors on a whim, we can do so using a format method call. And finally, we printed out the lyrics. So in conclusion, you can use the format method on any string to do any C-style string formatting, or if you want to call it Java-style string formatting, you can do so. %s is probably one of the more popular ones. %d is probably the second one. And this will cause a replacement of the %s using whatever repeated parameters that you use in the format method. Positions in a format can be performed with %, and then you place the position, $, and whatever it is, the format that you want. This is no different than it is in Java. In this section, we'll be covering the wonderful world of Scala string interpolation. Big word, basic idea. With string interpolation, we can replace any word from within a context. And a context could be a class, it could be an object, it could be a script, anything that is outside of its line. So let's create a file called stringinterpolation.scala and try some of this string interpolation out. Let's set up a val. A is equal to 99. And some of you may be familiar with this song. This is a lyric from a song called 99 Love Balloons. And we are going to start off with the letter S. This S comes before the string. And in order to use string interpolation, we require this S. Now that we've established that this is going to use string interpolation, I am going to bring in an A, surrounded in braces. And the rest of the lyric goes, 99 love balloons floating in the summer sky. This almost looks like formatting. The only difference is that we are going to use a $sign. We may or may not use braces, and we're going to replace A with whatever A is within the context of this line. So in the context, meaning around its general area, there is an A. We are going to take that A and it will be replaced right in here. Let's save this file. Again, we want to call this string interpolation.scala. And let's run it. As we see here, the 99, which was val A, is equal to 99, which was in the context. It's going to take that 99 and replace the A with that particular number. Because we are only referring to one value, we can omit the braces. Let's go back to the code and show you what I'm talking about. I'm only referring to A, so the braces aren't absolutely necessary. We could just simply say $A. Let's save it and run it now on the console. Shows the same thing. Let's go back to our code. Be warned, though, that once you try to call any method on the interpolated object, perhaps things can go wrong. And let's say that for this particular number, let's say I want to add 3. Now, because we're doing it this way, we're going to get a result we're not expecting. I went ahead and saved this. Let's go over to the command line and see the results. It says here this is 99 plus 3, but what I really wanted to do is I wanted to add the 3 to the 99. So that did not work. So let's go back to our code and put braces around there. Save it, and let's go to the command line and run it. And finally, we'll have 102 love balloons floating in the summer sky. There's also a way to format a string using the string format rules that we did in our previous section, and interpolate that in one fell motion using what's called the F interpolator. So let's go back to our code. In this example, I'd like to set up a value called ticket cost. This will be an int. I'd like to set up a band name, bring in an 80s band, and I would like to do an interpolation. So I'd like to print line F. Now this is going to be a little bit different. Take a look here. I am starting with an F. I am not starting with an S. The band name, and I want to interpolate this as a string. I can use different formats with the F interpolator. Tickets are probably, and for a $sign, now a $sign is going to be tricky because a $sign is the character that escapes for string interpolation. So in order to create a $sign, I need to put two $signs in order to create that. Then next, I want to bring in the ticket cost, but I want to format this as a float. So let's say 1 digit dot 2 for the decimal point and as a floating number. This is the F interpolator to do formatting. Let's save it and let's run it to see the results. I have an exception here. Ticket cost is not found, likely because I called it tickets cost. Let's save it, fix the issue, run it again. So with the F interpolator, we were able to bring in the string and we were able to bring in the number value, and we formatted it using the F interpolator and using this format. So we wanted to interpolate 50, which if you recall was an integer, but we wished to format that using a decimal point. So using 1.2f. The 1.2f created for us this 50.00. Let's go back to our code and review. Again, these are two different interpolators. One is just an S interpolator where we get the A and we do something with it. The F interpolator, we can still get information from within the context. But what's different about this is that we can format it according to the formatting rules of string format. Now let's change things up a bit. Let's say we have the ticket cost, we have the band name, and what I'd like to do is let's do a %, change things up a bit, and I'm going to have a % increase. Let's say a % increase of 20, and as the music genre, let's say that this would be new wave. I'm going to bring that print line down here, but I'm going to change things a bit. Let's say we want to say the band names tickets are probably this cost. And after this, let's create a new line. And I'm going to say that's A. Let's bring in our percent increase here. I need to do 2% in order to create 1% name. Just because percent is used for formatting, so two of them is going to be the escape to create the percent. And I'll just say this is a bump because everyone likes this particular music genre. It's a fairly large format we have here. Let's save this and run it, and let's see the result. So we have our new line. We use %n for our new line. It states here the Psychedelic Furs tickets are probably $50. That's a 20% bump because everyone likes New Wave. Now let's say we didn't want to do the new line. Let's say that we wanted to separate this up a bit. In fact, let me go ahead and bring this down and show you how to do this with a smart string. So this will be an F interpolator using the F interpolator, using a smart string. Now, whether we're using an S interpolator or we're using an F interpolator, we can use a smart string with those interpolators. So I'm going to use the F interpolator using a smart string. And in our case here, I don't want to do this %n. I would just rather use a smart string to format it. Let's put a pipe there and finally call strip margin. And this says that's a % increase bump because everyone likes a certain music genre. We'll need one paren here, because we'll need the strip margin to apply to that smart string. And there we go. Let's run this. So again, what's different about this one is instead of using that %n, I wish to use a smart string. I am preceding all of this with the letter F, causing this to be an F interpolator, and everything will be replaced by what is in the context. Band name is from the context, ticket cost is from the context, % increase is, and so is music genre. It's a little cleaner, and this just goes to show you we have a lot of tools at our disposal to display output. Let's save it and run it. Let's go back to our code and review. We have multiple ways to run the string interpolator. One is the S interpolator that just brings values in from the context. F interpolator brings values in from the context, and we can format it along the way. We can also apply this using a smart string. So in conclusion, string interpolation performs variable replacement within a string. All that is required is an S or an F before a string. Braces may be required to surround an evaluation. We saw that with our A+3 example. You can use F interpolators in conjunction with the classic C style or Java style string formatting. And string interpolation also works great with Scala smart strings. In this section, we'll be covering basic methods. In Java, there is a differentiation between methods and functions. In this session, we're only going to be talking about methods. Methods belong to a context. And in an object-oriented programming language like Java, that context is a class. There are different contexts actually in Scala: a class, an object, a script, or another method. In Scala, a method starts out with a keyword called def. A method will always start with def. In our example, we're going to create a file called basicmethods.scala, and we'll be creating a method called add that will add two integers together. What we're going to start off with is we're going to do this in the most inefficient way possible. Let's get started. This method, we are going to create a file called basicmethods.scala, and here we are. And we're going to start off with the keyword def. Again, def is the thing that starts off every method. We're going to give our method a name called add, and now we're going to add it with some parameters. So how do we do parameters in a method? Well, if you're coming in from Java, or perhaps some other language, you're probably used to something like this, where you specify the type, space, and the parameter name. In Scala, we're actually going to do the reverse. We're going to do x, the type, comma, a new parameter name, and the type. What comes afterward is the return type. And in this case, the return type is int. If you're coming in from Java, you're going to expect that the return type come over here. But that's not the case in Scala. In Scala, the return type comes at the end. Now, as a warning, this is the most important part of a method, and it is the equals. That means that we are stating that this method is going to return something. Now, let's go ahead and add a brace, and we'll give it a return x plus y. Everything that happens within here is the body of the method. The / is the way we do comments. And finally, we're going to close the brace. Next, we'll go ahead and print line, and let's see what happens when we add 6 and 7 together. Save the file. Now let's go over to the terminal, and let's see how this looks. Looks like we're on the right track. Now let's go back to the source code and get rid of some unnecessary items. First off, the keyword return is actually unnecessary. Scala programmers hardly ever use it. We could also get rid of these parentheses, they're not required anymore. There is really only one line in this method, so we could bring that up to the top. Let's get rid of this comment. These braces are unnecessary. And the return type can also be inferred. Since x is an int and a y is an int, and the operation of adding the two together will also return to an int, the type inferencer during compilation will already know that the return type is an int. Therefore, the return type here is absolutely unnecessary. Be careful though, there are times where we will actually need a return type, and those required times are the following. Here's a slide called Reasons to Include Return Types. One is perhaps you want to make your intentions clear. Two, perhaps the type inferencer will assume the wrong type, and it'll be up to you to settle on a type. Three, your method is being called recursively. And finally, your method might be overloaded and a return type is required so as to distinguish this method from other methods with the same name. Now, since none of these reasons are applicable to our method, let's get rid of the return type. Let's save it and do a sanity check. Fantastic. Let's go back to the source code. Now let's add a little complication to a method. Let's bring in an if statement from a few sections back and make that into a method. Again, I'm going to start off with def. This is a different method, and I'm going to call this one number status. It has one parameter called n, it's of a type int. And again, the important part, I need an equals. Let's do a brace first and do an if statement. If a was less than 10, then we returned less than 10. Else, if a is greater than 10, then we have greater than 10. Otherwise, it is 10. We had something similar to this a while ago, and I'm going to finish off with a brace. Now, we didn't specify a return type, and in fact, we don't even need these braces. Remember the if statement? We could just treat it as one single statement. But in this case, we have an if statement, and the last evaluated statement, as I mentioned before, will determine the return type. This isn't a trick question. The return type will be a string. In 3 different branches, as you see here, we have an if, an else if, and an else. These are 3 different branches, and in each branch, we are returning a string. Therefore, this method will take a int type and return a string. In fact, if we copy this code and bring it over to a REPL, what I like about the REPL, it always shows what the compiler is doing and what it's looking at. Let me show you an example. So I'm going to copy this code, and I'm going to bring it over to the REPL. I'm going to call paste in the REPL. This is paste mode, and I'm going to bring the code in here. Here's the number status. As stated, I'm going to hit Control D to finish. I called it A instead of N. Let me go ahead and just change that to A. Embrace our errors, recopy this, and do it again. Okay, as you can see here, we have a number status. We're bringing in an int, and we are returning a string. Even though I didn't explicitly declare it, as you can see here, since there are 3 branches and all of those, last evaluated statement under each one of these branches will return a string. Therefore, the type inferencer is going to go ahead and strongly assume that this return type is going to be a string. Let's go back to our code and let's see what we've done. So we create a method called add, takes two ints. We have the equal. We need the equal because this specifies that we are returning something, and we're adding x and y together. The next thing, we have a number status where we bring in an int, and we have three branches, an if, an else if, and an else. At the end of these branches, each branch, the return type is a string. Therefore, the return type for the entire method is a string. So in conclusion, methods are defined using a def, and they're always defined using a def. Methods are not to be confused with functions. The return keyword is unnecessary because the last evaluated statement will be returned. Most of the time you could omit the return type in methods unless you need it for clarity to override the type inferencer, whether you're using recursion or whether you're doing method overloading. In this section, we need to understand a little bit of types before we could discuss more about methods and return types. A type is a class, trait, primitive, or an object in Scala. A class, for those who don't know, is a code template or blueprint that describes what the objects created from those blueprints will look like. Here's an image of an architect. This architect is the virtual machine. And what the virtual machine will do is it will class load a template or a blueprint from either the file system or the network. The whole process is called class loading. Once a class is loaded onto the JVM, given that blueprint or class, the VM can create multiple objects from that particular template. That template is a type. Therefore, what else is a type? An int is a type, string is a type. If we create a class called car would be a type. If we create a class called invoice.json_serializer, then invoice.json_serializer would be a type. List, set, a map, serializable interface, those are all types. Scala is a static type language, and all types need to be known at compile time, and all types are under the control of what is called the type system. As a Scala programmer, it is up to you to make sure that all the types match, very much like a puzzle. Let's do some code. I'm going to head over to the editor. In this file, I'm going to create a method called add, which will take in two ints and return an int, and obviously it's going to take those ints and add them. I'm going to create another method called subtract, which brings in two ints and returns an int. And I'm going to use these methods together, and I'm going to match the types. I'm going to do this all in a file called types.scala. Okay, so again here we subtract. The subtract returns an int, therefore add requires two ints, so we know that add requires two ints, subtract is going to return int. Therefore, the type system goddess is pleased with our design and will not destroy us in hot molten lava. So let's go ahead and run this. And let's see what this gives us. Okay, so we have our number. Now let's change subtract to take in different types and return a different type to see what happens. Now what we're doing is we changed int to double. That means via type inference, the x minus y is going to return a double. So therefore the types are not going to match because subtract returns double, and what we're trying to do is we're trying to give add two different doubles. Let's run it. Okay, so we end up with a couple of type mismatch errors. Type system goddess is displeased with our attempts and punishes us with these particular exceptions. So types are good. It keeps us from making mistakes in our logic. In a moment of reflection, it could be that we didn't want to perform this operation. After all, we're trying to take the double type from a subtraction and shove it into a method that takes an int. So maybe we wanted to take the double and either truncate it or round it while we're thinking about it. And this is why static typing is so important. It allows us to reflect on our code. Maybe it is something we wanted, maybe it isn't something that we wanted after all. So let's go back to our code and try to make these types match. Now this is just an example, and yes, the obvious answer would be, why don't I use ints to ints? But let's say for the specification for subtract, we could only use doubles. And we need to find some way for these two methods to work together. So let's try perhaps a truncation here. So let's say within this subtract, I want to do a toInt. Let's run it. That works. Every number type has a method that converts from one number type to another. toByte, toShort, toInt, toDouble, toChar, etc. For a conversion from a double to an int, this is purely a truncation. Let's go over to the REPL and let me show you what that means. So let's say that we have 10.0, and this is going to be a double. And let's say that we're going to take 10.0 and we are going to truncate it. If this looks confusing, let's wrap the 10.0 in a paren. So we're going to take a double and call toInt. That looks great. So this is a truncation. We could also do a round, but there's a problem with this. This 10.0.round is going to return a long. And remember, the types should match. What we want out of this is an int. One thing that we could do is we could possibly do a 10.0, round that, and then do a toInt. And this will give us the number that we're looking for and the type that we are looking for. But this comes with a warning. Long is 64 bits and int is 32. So we may lose some information if we do this conversion. For example, let's say I have a val called long value. So what I'm going to do here is I'm going to take this long value and create a very large number and round it, and then I'm going to call toInt. Okay, so we have this long value, 203.949, etc. .4332. Then we call round on it, so it's going to round it out, and it does so fairly nicely. Once I have the round number, remember this is a long, but if I call toInt on this, then we have an issue because int only takes so much space. It takes 32 bits. Long is 64 bits, so there's going to be a loss of information. And because the first bit is likely going to have a sign on it, this is why the number is negative. So do we have another choice? Well, there's something called method overloading that we could perform to accept different types so that it wouldn't lose any of the data. There are some other types like big int and big decimal as well. So we can cross that bridge a little bit later when we talk about overloaded methods. But back to our problem, let's say that we're okay with this. Let's say we'll run the risk that some of these values will be too large, and therefore it's acceptable for now. So let's go back to our code and make that change. Remember, the whole point of this lesson is about type matching, not particularly right now about whether we're getting the right answer or not. So given this add, I have the toInt, this is truncating. Let's say that I want to make all of these a round and a round. Let's run it. Okay, type system got us as most pleased. Types match, whether your program works to your specification. Again, we are running the risk of possibly taking a really large number and not bringing it down correctly. But as far as the types matching, let's go back to our code and review that. It works correctly. Again, add takes two ints, subtract returns doubles, therefore we need to make the types match. Types have relationships. Scala is not only a functional programming language, but it's also an object-oriented language. In fact, I'd like to argue that it's even more an object-oriented language than Java. In Java, there are objects and there are primitives. In Scala, you could treat everything like an object, and if you can do that, you can treat all numbers, characters, Booleans as types. Every type has a relationship and is a member of an illustrious family tree. So let's take a look at this family tree. Unlike humans, procreation, an object-oriented system does not require two parents, just one. In Scala, any is the parent of all types. AnyVal is the parent of all numbers, Booleans, characters. For the Java people migrating to Scala, that means that all your primitives have a parent, and that parent is AnyVal. AnyRef is any other type that has a class. Whether Scala created it, whether Java created it, or whether you created it in either Java or Scala. Here's a fuller graph. Again, any is the topmost parent, AnyVal is the parent for all primitives, and AnyRef is the parent of all objects. It's also worth noting that for the Java programmers coming in, Java lang object is going to be semantically the same as AnyRef. Again, here's AnyVal. That is going to be the supertype of all primitives. So types are templates that make up an object. Primitives are also types in Scala, int, short, byte, character, Booleans, etc. Types need to be matched up like a puzzle. If it isn't, the type system at compile time will tell you there's a type mismatch. Every type is in a relationship. Any is the parent for all types, AnyVal is the parent for all primitives, and AnyRef is the parent for all Scala, Java, and custom objects that you create. In this section, we'll be discussing methods returning different types and what the type inferencer will decide is the best return type. Scala's type inferencer will always make the best choice given the information that it has. Since we know how return types work with methods, and we generally know about types in Scala and how everything eventually extends from either AnyVal or AnyRef, and we also know that AnyVal and AnyRef extend from any from the previous session. Here is a class diagram from the previous session as a reminder. AnyVal extends from any, AnyRef extends from any. AnyVal is the superclass for all primitives, and AnyRef is the superclass for all classes. Here it is again. Here's any, AnyVal, AnyRef. Again, AnyVal is the superclass for all primitives. Given this now, we'll understand what will happen if we do something like this. So let's go over to the editor and give this a try. Let's say I want to create a method called add given two ints. What I'd like to do is I'd like to ask the question if x is greater than 10, and I'd like to return. Okay, so I have method add bringing in two ints. If x is greater than 10, then do the summation but return it as a string. Otherwise, do the addition. Finally, let's do a print line and save this in a file called differentreturntypes.scala. Now I'm going to run it. So it does what we are expecting. We don't know though if this 14 is really a string or an int. What do you think the return type of this actually is? In order to do that, let's look back at our chart, but this time let's include string. Here is string. Remember, any class will extend from AnyRef. And of course, AnyRef is a child of any. Int is a child of AnyVal, and that is, of course, a child of any. Now we have to determine what is the common parent for both string and int. Well, that would be any. Therefore, the return type for the method we just created is any. To verify that, let's copy the code and put that into a REPL. As you can see, the return type for the add is any. So in conclusion, types inside of a method, and this could also be applied to functions as we'll discuss later, will be inferred. The type inferencer will make its best judgment based on what is available. If types are different, it will find a common ancestor and use that type. In this section, we'll be discussing unit, what it means, and its conventions. Let's go over the REPL to get started with unit. There's a value we can create. It's an open paren and close paren. This could be assigned. Now this type is inferred, and it is called a unit. We could be explicit about it if we want to. Unit is something that you get when there's nothing to give. The analogy in Java is that this is a void, or what you consider to be a void. When would we use unit? Well, you've already used one, and it's called printline. So let's go over to the documentation. By the way, if you want to take a look at the documentation, it's at this address. The API is at scala-lang.org/API/current. Current will get you the latest API for your perusal. And what we're going to look at is called the predef. Now, predef is an object. We haven't discussed objects yet, but a predef is something that is inherited in every Scala class object file that there is out there. So it's automatically imported. So let's take a look at the predef, or a little bit of the predef. As you can see, there's print that takes an any and it returns a unit. We did print line before. There's printf. We also did that one before. This one shows a unit. Here's print line. This takes in an any. You know what any is now. That is the parent of everything. So that means that we can give print line any type that we want, and it's going to print it out. And this is going to return a unit. The type is unit, meaning, again, it's analogous to void. We're not getting anything in return. So in fact, when we type this into the REPL, let's go back to the REPL. If we type in print line Scala rocks, in fact, instead of just that, let's assign it to something. We see that the return type, after we did a print line Scala rocks and assign it to A, we see that A is of a type. That type happens to be a unit. If you go to Java, for example, you can't do a system out print line call and assign it elsewhere, but in Scala you can, because unit is a type. It is assignable. So where's unit in our hierarchy chart? There it is. It's actually thought of as a primitive, and it is a subtype of AnyVal. So keep that in mind. Let's do something else. I'm going to go back to our REPL. So again, remember this right here. We have Scala unit, and that is a child of AnyVal. It is considered to Scala programmers a primitive. So in our REPL, I'm going to do an add, much like the tired old example we've been doing up to this point. But what I'd like to do inside of this method is ask, well, if x is greater than 10, then we wish to return a print line. Again, it may seem kind of strange that we're returning a print line, but since we know that print line is returning a unit, we know that that unit will then be the return value from it. I'm going to have an else case. In case it is not greater than 10, then we'd like to return the summation, and we'll close that up. So again, print line returns a unit, x plus y naturally returns an int. And what do we have here? AnyVal. Let's go over to our hierarchy chart, take a look at this again. Both unit and int, remember int would have been the type given x plus y. X plus y would have returned an int, but print line returns a unit. Remember, unit is something that is assignable. So therefore, in something like this, if we're giving two different types, then the return type of the method said it was AnyVal. Why is it AnyVal? Because it is the parent of both int and unit. Programming to a type system is all about putting the pieces into a puzzle. If the types match, then it will work. So let's get a little crazy. For a no real life but purely academic example, let's give something else a try. I'm going to go back to the REPL and create a method called nonsense, and we're going to bring in a unit. And we're going to return an int in this case, and the return will be a 40. As you can see here, the signature for this method, nonsense, is that we are receiving a unit and we are returning an int. So if we wish to call it, we'd have to call it with a parens, and we would have to make sure that we tell Scala what we're trying to do is we're trying to give it a unit. So we get a 40 out of it. We're giving it the value of the open paren and close paren, and we're getting 40 back. Now, why did I do such a dumb example? To show you that unit is an object and it can be used anywhere. So imagine putting void into a method in a programming language like Java. It's not going to work, but in Scala, if you want to think about it this way, unit is an object and it has a type, and we can just treat it like any other object. There isn't much you can do with unit. It is what it is. It's just this plain object that you can move about. It is just a representation of a no value. So let's go back to a simpler time when we worked on a basic method and try something else. Let's go to our editor. So I'm going to create, in our editor, I'm going to create a method called add, which takes two ints and obviously returns x plus y for it. I'm going to save this in a file called unitmethods.scala. Now this is a simple method in Scala that adds two numbers. I mentioned this in the basic methods video, that when an equals is used, that it states that we want to return something. Let me add some braces. The reason I brought this up is because a common mistake for Scala programmers, especially those that come from the land of Java, is that they often forget to include this equals at the end of the method. Remember, equals means that we want to return something from a method. So let me do a bad add. The method up top is correct. The method down below called bad add is incorrect. I'm going to do a print line on this bad add. Now I'm going to run it. Okay, so this returns an open paren and a close paren. You know what that is? That's a unit. Remember I mentioned the open paren and close paren is the value for the unit type. Now when you see that, don't panic. It's just an object that tells us we got nothing from it. In other words, it is a void. If we wanted to be explicit about our bad add, let's say it was intentional that we wanted to return a unit, we could just say, well, we want to return a unit. Let's go back to our code. Again, if we wanted to be intentional about it, let's call this one something different. I'm going to call this add unit. That takes a x and a y, but this time what I want to do is I want to be explicit about it and state, I know what I'm doing, and this is going to be returning a unit. In fact, I could use the equals here. I am returning something, and in this case, what I'm returning is actually a unit. So in my case now, I have add unit, takes in 2 ints, returns a unit. I am being explicit about that. I am using the equals. I am returning something. Remember, unit is an object. I can return it. I'm adding x plus y, but that's irrelevant because what I'm returning out of here is nothing. Let's run this. Same thing when we run it. Again, I didn't call it bad add because this was intentional. I did do it on purpose. I called it add unit. But remember, the point here is whenever you see the open paren, close paren, it is a unit. The type is unit. There is only one value for unit, and that's the open paren and close paren. Unit will be used sparingly as a return type in Scala. In pure functional languages, you won't see it at all. Whenever there's a return type of unit, it likely has a pure side effect. This has nothing to do with pharmaceuticals. A side effect is something that happens to the outside world. Perhaps something like printing to a screen, writing to a file system, sending items over a network. When we're printing to a screen, that's the case of a print line. That is a side effect that happens. Sometimes we're even changing the state of an object. Changing the state of an object is also considered a side effect. Let's try another sample of code. Let's go back to our editor. I'm going to create a new file called sideEffectState to show you what I mean by state. In this example, I'm going to create a var. Remember, var means that there's a side effect. There is something that is mutable. Created var a is equal to 0. I created a method called sideEffect. In fact, take a look here. I did not include an equals. This is going to return a unit. As I mentioned before, it is up to me whether I want to declare this returning a unit, or I could just leave the return type out. And if I am returning a unit, I can leave the equal sign out. This is changing the state of an object. Again, I have a var. var is usually an indication that something is mutable. Also an indication that sometime down the line there is a change in state. Now, you don't have to be too stringent on avoiding state. Although some functional programming purists may disagree, there is a topic called state monad, a functional design pattern that you can use to hold state by avoiding a lot of these side effects. That's not covered in this series, but in time it may be something you want to learn up on after you get some more functional knowledge in that squishy brain of yours. I will mention this. The whole idea for Scala is to bring over Java programmers, to make it comfortable for Java programmers. So keep that in mind. You're not doing things wrong if you're bringing in your object-oriented knowledge over it, you're bringing your mutable knowledge over. Scala will work with you. Again, over time, you're going to learn some other concepts, and once you learn those concepts, it could very well be that you don't like these side effects and you wish to implement a lot of these functional design patterns to avoid them. So in conclusion, units don't give you anything. They are analogous to Java's void, and units are actually objects. The unit full type name is scala.unit from the Scala package. Unit has one value, the open paren and close paren, and whenever you see the open paren and close paren, that is a unit. Recursive programming is essential in functional programming. It is strategically recalling a method to perform a task. In this section, we'll create a method that is called recursively onto itself. Let's start off with a file. We're going to call it basicrecursion.scala. Let's create a simple recursive method to do recursion. I think maybe most of you will know what a factorial is, but if not, factorial is the product of all the positive integers less than or equal to n, given whatever n is. A factorial is usually denoted as a number with an exclamation point, and as a special rule, the factorial of 0 is 1. So let's get started. I'm going to head over to the editor. Again, if we have a factorial of 5, that's going to have to be 5 times 4 times 3 times 2 times 1. Factorial, again, of zeros, it has to be 1. Factorial of 1 is going to be a 1. So let's get started. Okay, so here's the first line. Def factorial, we're going to bring in an n. It's an int. And we are going to return something. But first of all, we need a base case. And the base case is the simplest thing that we can do. How do we code that? Well, our base case is whether it's 0 or if it's 1, then the answer has to be 1. So let's do that. So in case it is 0 or in case it is 1, then it'll be 1. Otherwise, we're going to take n, whatever number it is. So if we give it 5, we're going to say 5 times. Now what we're going to do is call factorial with a deduction. Let's do a print line and save this file. Let's run it. Okay, so we end up with an error. Error, recursive method factorial needs a result type. This happens to be one of the rules for recursion. Return type must be declared. Let's fix that. We do need an int. We do need to declare the return type. Let's save it and run it. That's fantastic. It works. We have a recursive method. Only problem now is that this doesn't go very far. Let's add another item. Let's go back to the editor. Instead of 5, let's do 100. Not a huge request. Let's give it a try. Interesting. 0. It overflows, and this is not right. So let's change things around. Let's do a big int. Big int happens to be a class that has storage and enough storage that we can store very large numbers. It just holds more information. And believe it or not, this is all that is required. Just change the types. Though it's tough to see right now, there's something good happening at the compiler level. And for those coming in from Java, you would understand. We didn't have to change the methods or the structure that much of the method because big int has the same method names as int. In other words, big int has a star. Big int has a subtraction. Big int has equality. It can also convert the 1 into a big int 1 automatically. What that means for you is you can express yourself faster without paying too much consequence on changing the type being used. Let's run this. Nice. Get a very big number, so therefore the factorial for 100 is 933, etc. Now let's give it something harder to work on. Let's go back to the editor. Just one more 0. Let's run it. Looking very good. Now, of course, this is the factorial of 1000. Of course, this is going to be a much larger number. Let's give it even something harder to work on. Let's go back to the editor. And kablooey. At some point, we blew the stack. Recursion only goes so far before the stack that handles the recursion blows up. You could adjust the stack at the command line for the size of the stack, but that is unnecessary because we have another strategy. We'll rewrite this in something called a tail recursive optimization in the next session. Let's see if we can scroll up. It could very well be that we aren't going to be able to see the first part of this error, but it is a stack overflow exception. So in conclusion, methods can be recursive and call themselves. Let's take a look at that again. It's worth looking at this again. Right here is where the recursion happened. We're calling factorial, but with a different number. We're subtracting 1 from it. But this is a method calling itself. So recursive methods call themselves. They require the return type in the method signature. Recursive methods can be infinite if written correctly, or have a base case where everything stops. Recursive methods have so much stack to use before it blows up. There's only a limited amount of space. And you may need to reconsider the decision to use tail recursive calls. In our last session, Recursion, we created a method called factorial. If you're just joining this session a la carte, review the last session. What we'll be doing in this session is redesigning the factorial method to be a tail recursive method. Let's go back to the file called basicrecursion.scala. It almost worked well until we called it with a fairly large number like 10,000. If you recall, 5 worked out really well initially. We had problems with 100 and 1000, mostly because we were just dealing with int, and int only has limited size to work with. So what we had to do was beef that up to a big int, which is an object that stores more information and represents an integer. Now what I'd like to do is save this file as another file called tailcallrecursion.scala and open that file so we can make changes. Okay, everything's saved. Now before we begin, there's an annotation we can use called Scala annotation tailrec. Annotation is a metadata that the compiler uses so that we can change the way the code is compiled or used at runtime. Annotations will not have any direct effect on how the code operates. So let's get started. Here's the @annotation, scala.annotation.tailrec. The scala.annotation you see there is a package. Packages, for those who don't have a Java background, are addresses of the class, much like the addresses of your home or place of business. In other languages like Ruby or Haskell, they're called modules. Typically in the JVM world, they are the reverse domain name of the company or entity that created the code. If you work for a company called XYZ Corp, for example, then the package would likely be called com.xyz Corp. If you work on a project called Project A at the XYZ Corp company, then a possible package would be com.xyz Corp Project A. At compilation, packages are made into folders where the class, or in this case, the annotation, would reside. In Scala, all constructs are a member of the Scala package, either directly or indirectly. The full name for Scala annotation tailrec is called the fully qualified name of the annotation. If we don't want to include the fully qualified name of the annotation above the method, we could import the annotation so that we just call the annotation name without including the entire package. So let's go ahead and do that. Now, when we try to compile this or run it, since it is a script, we get to see what a nice handy utility the @tailrec is. It's going to tell us that this code does not meet a requirement. Let's give it a try. It tells us that this code is not tail recursive. To make this tail recursive, we need to ensure that after the recursive call has been made, that there are no further operations on what has been returned. We obviously violate this rule. Let's go back to the code and take a look. We violate this rule because we are calling factorial, and right after we're calling factorial, we are multiplying. We're doing an operation after the factorial is returned. We have to make sure that whatever factorial returns is immediately returned from the method. We can do this with an accumulator. An accumulator is an object that will hold the running total, in this case the running factorial, with each recursive iteration. So let's change this code around. So I'm going to add the accumulator. This is an accumulator that has a big int type. In our base case, whether n is 0 or 1, what I'd like to do is instead of returning 1, I would like to return the accumulator. Now when I call factorial, I'm going to get rid of the n star because we want to make this tail call recursive. And what I'd like to do here is multiply the accumulator by n. Since we made changes to the method parameters, we also need to make change on how the factorial method is invoked. Now that factorial requires 2 parameters, I need to make sure that there is a second parameter to each one. With those simple changes, we can run the script and see what happens. This works. Let's take a look. The bottom one right here is the factorial for 10,000. Pretty big number. Here's the factorial for 1,000. Here it is for 100. And here it is for 5. This works, and this is just another way to look at the same problem. What happened? Let's take a look back at the code. This is a compile time trick. If your recursion is modeled in a tail recursive way, then the Scala compile will optimize the code for you in a loop so that the stack is rarely filled. This process has an acronym, TCO, or tail call optimization. Of course, one problem that we have is that we have to keep calling our factorial method with 1 every time we want to call it. In other words, we have this one, this number 1, and this number 1. Let's create a method that does this for us so that we don't have to call it over and over again with the number 1. In order to do that, I'm going to change the factorial to a method name called fact. That way, the main method that we usually interact with will still be called factorial. Factorial will bring in a number, and when we call that number, we will then call the method with that number and the number 1. Now, we can get rid of the 1s. Let's run it and make sure all this works. Looks great. We have our 10,000. Again, here's our 1,000 coming up here soon. There's the 1,000. There's the factorial for 100. And finally, the factorial for 5. Looks great. Let's review the code. So we have our factorial method that brings in an int, and we call fact. Now up here under fact, here's the method fact. This is our recursive call. We refactored it to make it a tail recursive call. There are no operations being made on this method after it returns, and here is the tail rec annotation. In the next section, we'll do some other refactoring by putting one method into another. If your recursive method continually makes calls to themselves, they may run out of stack memory. A strategy you could use is to convert your recursive method into a tail recursive method. The recursive method, after being evaluated, must immediately be returned. And finally, in conclusion, you can also use an @tailRec annotation from the Scala annotation package for any compilation assistance into making sure that your method is indeed tail recursive. In our last session, we have a tail recursive method called fact, and that is used by another method called factorial. Fact is our tail recursive call, and all this was in a file called tailcallRecursion.scala. Let's open that up and review. So here's that factorial method that I was referring to you about. This brings in an int. We take that int and we call the method fact. Once we call the method fact, we have the number that we wish to get a factorial of, and we have an accumulator that is going to keep our running total for us. If n is 0 or n is 1, the base case will state that we will just return whatever has been accumulated up to this point. Otherwise, we will deduct 1 from n, and for each succession, we will multiply the accumulator times n. So what I'd like to do is refactor this a little bit, and I'm going to save this into a file called Methods in Methods.scala. A feature that I really like about Scala is the ability to take a method and shove it into another method. Use case would be if you have a method that assists purely with one method and nothing else. One such method would be our fact method. It is not needed anywhere else, and all the interaction can be done by our factorial method, since that is the public interface. So let's try that. Okay, did some cleanup along the way, and what we did is we took one method inside of another method. Again, factorial is going to be the public face in all this. The fact can be hidden away inside of another method. It looks great, everything in its place. So this may be a feature that for the Java programmer you'll not see in the Java programming language, but this makes things a lot cleaner. So in conclusion, methods in Scala can be hidden inside of another method. Use case would be the method inside does not interact with the outside world, and it is only for exclusive access to that inner method. In a previous session, bending val and var to your will, we created some values and variables with some nifty tricks that allow us to express ourselves when it came to naming. We can take those tricks and apply them to methods. Now, much like vals and vars, we also have spaces and other what are called opchar or operational character codes in a method if the method name is surrounded by a backtick. Now, if you need a reminder before we do this what an operational character is or an opchar is, there are a few links you can visit. This is from unicode.org. So a valid operational character is any Unicode character from U0020 to U007F. You could also include Unicode symbol math, and here's the category. Visit this website to see all the Unicode characters under the Unicode symbol of math. And here is the URL for Unicode symbol for other. So these characters are legitimate operational characters as well. So let's go to REPL and try some of these out. So let's say I want to create a method called summation of. And let's say I want to have a space between the words summation and of. Here's the method. There's the method name, summation of, between two backticks. The reason for this is because I have a space between summation and of. I'm bringing in two parameters. Both are ints. One's called x, one's called y. And as part of my implementation for this method, I'm just going to add them together. Now I need to call it. So I cannot call it like this. It's not going to know where summation is. It sees the of there, but it's going to interpret it as there's an object called summation that has a method called of. So that's not going to work out. So if we want to call it then we'd have to include the backticks. Now, if you also recall, we have an underscore, and anything after the underscore could also be an operational character. Let's try a sample of that. I'm going to hit Control-L to clear out my REPL. I'd like to create a method this time called Are We Liking Scala with a question mark at the end. Now, in the Java programming language, a question mark is not allowed as part of the method, but in Scala we can. But as long as we establish the underscore first, then we can use the question mark. So this is being interpreted as Are We Liking Scala underscore $Q mark, as you see here. This is a method that doesn't take any kind of parameter, but it is returning something, and in this case, it is a Boolean of true. It looks like a val or a var, but it really is a method. And at the Java bytecode level, it is going to be considered a method. Given that this is a method, we can attach this to a status. So we're using Are We Liking Scala as a method. The method's going to return a Boolean, placing it in an if clause, and if it is true, then we'll return nice, otherwise we'll return ah. Of course, we'd be remiss if we forgot to mention that if you want to make a reserved word a method name, you could do so, albeit it may be doing yourself and your team a disservice. But let's give it a try. Obviously, in this case, I'm going to create a method called return, but obviously this is a reserved word in both the Java programming language and in the Scala programming language. So let's say I'm going to be careless. I'm going to use a reserved word for a method, and this is going to take two doubles. Once we bring in these two doubles, I am going to take these two doubles and let's say add 4.0 and convert it to a string. So there's the method name called return. If I wanted to make use of it, obviously doing this may not work because Scala still sees return as a reserved word. So if I want to call the function instead of having it interpret as a reserved word, I would need to surround that with backticks. So in conclusion, methods can have spaces and other valid identifier characters, including operational characters, if they are surrounded by a backtick. Methods may be referenced without a backtick if they are not reserved or do not contain any spaces, otherwise we'll need to include the backticks. Any method without a backtick can include an operational character if followed by an underscore. In this session, we will discuss operator overloading. As in languages like C++, operator overloading gives us the power to name our own methods as operators like plus, minus, multiply, or asterisk, or slash for divide. This power comes also with Scala, but be warned, with great power comes great responsibility. Operator overloading should semantically make sense to your domain, typically without having to look up its meaning. So let's go to REPL and give this a try. Alright, here we are in the REPL, and let's say I want to create a method called add. Done this method over and over. So that works out fine, and of course we can just call add with it. But what if instead of add, I wanted to call it plus? I can do so. Now there are better ways to go about this, like using an infix method, which we'll cover a little bit later. But as it is currently, this works. We know what plus is, we know the semantic meaning of it, and we can intuitively make sense of what it is. I also brought this into REPL for a reason, because we get to see the type. And here's the type signature of the method. See that $plus? The plus is actually the name of the method internally. To you, the programmer, it's just the plus sign. But internally it's called $plus. Let's take a look at another example. This works, but this is just me. Semantically, it doesn't make much sense. No intuition can help, and try looking this up on a Google, Yahoo, or Bing when someone wants to try to know what this is. This is invocable, but again, this is something that's really hard to look up. So what can we use? Well, we could use all the operational characters, or opchars, as method names. And here again, just to jog your memory, are the references as to what opchars we can use. Again, unicode.org. The Unicode characters from 0020 to 007F are valid operational characters. You could also use symbol math, and you could also use symbol other. Any symbol that is listed on here can be used as an operator overload. By the way, did you know you are already using operator overloading? Let's go back to the REPL. Let me hit Control-L, clear up the screen. Remember this? It just seems like we're adding 3 to 10. But remember that we could treat all of Scala as if it were an object-oriented language. In other words, that means from our point of view, we are using the plus method, remember operator overloading plus method, on the 3 object and calling it with 10 as the method parameter. In fact, this is listed in the Scala documentation. Here is Scala int in the Scala API. This is from Scala int from scalalang.org/API/current, and here it is. This is a method plus, which is inside of a class called int. We'll discuss classes shortly. And this takes a method parameter called int. Again, the plus sign is a method. So let's go back to that REPL. And here it is. Int has a method called plus, and we are merely invoking 10 to the object 3. Remember our recursion method that we completed and refactored in methods and methods? It was the factorial for a certain number. We used recursion and we put a method inside of a method. We also used tailrec and designed that using a tail recursive call. Remember how we didn't have to do much when we changed from an int to a big int? Let's reacquaint ourselves with that file called methods in methods. Here it is again. Remember, we had int before, but all I did was change it to a big int. And if you remember right, this didn't take much effort. I didn't have to change the method signatures, and the reason is big int also has a plus operator, a star operator, a slash operator for division and subtraction, etc. The same methods that were in int were also in big int. And that too was operator overloading. In other words, this minus right here happens to be the minus that is inside of big int. The star right here happens to be the star that is inside of big int. So in conclusion, operator overloading allows us to use operators as method names. Careful not to abuse this power. Operator overloading will interpret the name into a $sign with a suffix, so $sign with a name or $sign with a particular Unicode. And finally, you've been using operator overloading up to this point, probably without realizing it. In the case of int, in the case of double, in the case of big int, there are a lot of operators that are being used as an operator overload. In this session, we will discuss method overloading. Method overloading is the ability to use the same name for a method. Though not law, you would typically do so if the method performs the same operation but with different types. So let's create a script called methodoverloading.scala to see how all this works. We created our file. Now what I'm going to do is I'm going to create 3 different methods all with the same name. Here's the first one, add num. This will bring in an int. Once we take that int, which is an x, we're going to add 1 to it. Okay, so we created 3 different methods. One will bring in an int, one will bring in a double, and the other one will bring in a string. They all are called x. They don't need to be. In fact, why don't I just change that around so it's less confusing? It could be whatever you want to call it. And these are still overloaded methods. Now I'm going to invoke these. Let's create 3 print lines. So I have 3 print lines. One will call with 30. That means the first one will be invoked if I call the second one with 40.0. Since 40.0 is of a double type, the add num, the second one on my line 2, will be the one that's called. And for the third one, since I am invoking it with a string, the add num with a type of string is going to be the one that will get called. This is all based on types, and it's all based on parameters. Let's run it and give it a try. We see here that it's 31. Let's go back to the code. And the reason it's 31, we're calling add num with a type of int. And since 30 is of a type of int, the first method is the one that gets called. Therefore, we're just going to add 1 to it. Let's take a look at our second answer. Our second answer is 70.0. Let's go back. And the reason for that is that on our second call, we are calling 40.0, which is of a type double. Therefore, the second method on my line 2 is the one that gets invoked. And we are adding 30 to it. Let's go back. Third one says hello 19. The reason, let's go back to the code. We are invoking it with a string. Now, coincidentally, I put this in order, but the order really doesn't matter. It's all based on type. Again, as long as the method parameters are different, you could use the same method name, each with different implementations. Now, if the parameters are not different, the compiler will complain that the method names are ambiguous and that they are defined twice. So let's create some bad code next. I'm going to create a couple methods. Both of these will be called add10, and both of these will receive an int type. What's going to be different about this one is that the second add10 method will return a double. So if I try to invoke this, kind of see what's going to happen. I'm calling add10 with 40. Problem is, Scala doesn't know which add10 to call. Both of them accept an int. Let's save it and try it. First error says ambiguous reference to overloaded definition. Both method add10 of type int to double and add10 of type int to int. Second one states that the method add10 is defined twice. As far as the Scala compiler is concerned, it does look like that. There are two add10s, both that accept an integer. Of course, we had enough information on the type signature that would allow method overloading. So let's go back and change that. So what I mean is, if there's enough information, enough for it to be different, then it would know what to call. And in this case, let's say I want to change that second parameter in the second method to double. Save it. Let's go back and run it. Looks great. We get a 50. Let's go back to the source code and see why. We're calling 10 with 40, very much like addNum example we had up there. We're calling it with 40. Once we call it with 40, we are adding 10. So method overloading allows us to reuse the same method name for different reasons. The only thing is method parameters must be different in order to avoid any such conflict. In this section, we discuss named and default arguments. Others may call this named parameters or default parameters. According to the Scala specification, these are going to be discussed using the terms named and default arguments. Named arguments are a way of calling a method with our own order. So let's take a look at an example of a method, given a method that accepts a Boolean and returns 2 ints. And we'll call this process numbers, and let's see how this works. I'm going to create a file called named defaultargs.scala. And in here, I'm going to create a method called process numbers. And in here, I'm going to ask the question, if B, then X, otherwise Y. Okay, fairly straightforward. Let's do a print line just to get things going. Okay, I'm going to call it process numbers. I'm going to give it true. I'm going to give it 10, and I'm going to give it 41. Given this example, what should happen is that this should return 10. If it's true, in this case it is, then we will return 10. Okay, let's save this. Let's run it as a sanity check first. All right, we got our 10. Well, let's go back. Now, let's say for a particular reason we did not want to call the method with those arguments in that particular order. In Scala, we could specify the order with what are called name arguments. Merely state the name of the parameter name at an equals and provide it with the value in any order that you want. So for example, if I wanted to do, let's say I didn't want to do the Boolean here, but I wanted to specify that this will be X, this will be Y, and this will be true. B, this B right here, corresponds to this B right over here. X corresponds to X, and of course Y corresponds to the Y method parameter. This will invoke the method in order with the values given. Let's do another sanity check. I'm going to save the file, and I'm going to run the file. Great, it's still 10. This, again, is called named arguments. Now, Scala also provides what's called a default argument. Let's show an easy example. I'm going to create a method called add, takes two numbers. We've done this one plenty of times before. And of course, if we want to invoke it, nothing too crazy here. But what I could do is give it a default argument. And because I give it a default argument, I can call without it. Let's run it. First 10 was from the previous example. And we have a 7 and a 40 for this example. Let's go back. The reason this was 7, because obviously we're just adding 4 and 3 together. The method is called add. It's going to take two ints and add them together. On the second one, though, we give it a 30. And what happens is that when we call the method add, x is going to be assigned to 30, but since we did not explicitly call y in this example, y is going to be assigned to 10. Therefore, 30 plus 10 is equal to 40. The y:int equals to 10 is what is called a default argument. Now, where things get complicated are when the default argument is not the last parameter, but somewhere in the beginning. So let's revisit our process numbers example from above and give our Boolean method parameter a default argument. So in other words, coming back up here, let's say in our process numbers, we have a Boolean, and we're going to set that equal to true. So how do we call that? Well, if we call it with just the int values, something's going to go wrong. So let's give that a try. So we're just handing it over two numbers. Let's save it. Let's run it. Not enough arguments for the method process numbers. Doesn't know how to fit that in or make sense of it. In this case, it's saying unspecified value parameter y. So it's a little bit confused as to what's going on. Let's go back to our code. We're giving it 4 and 5, and because this is the way this is structured, I think what it's doing is it is thinking that the 4 is a Boolean, and the 5 is trying to match up with the x. And I'll be honest, this is an educated guess on my part as to what the compiler is doing. All I know is, yes, the compiler is confused, but let's go back to our output again, and this says unspecified value parameter y. So it has no idea where y is coming from. Types don't match, so the answer to this is a combination of named arguments and default arguments. So let's go back to our code and make this work. So here in the process numbers, we're giving it 4 and 5, and the compiler is confused. It doesn't know where to put the 4, doesn't know where to put the 5. And what we could do is use named arguments to help it out. Now the compiler knows how we're calling our method with only the ints. And all the time knowing that I'll be accepting the default argument of true for the Boolean. So let's save this, and let's see where we're at. Comes out as 4. Let's see the reason why. X is 4, Y is 5. By default, the Boolean is true. Since it is true, what will be returned is X. So in conclusion, named arguments allows us to invoke our method by method arguments. Named arguments also allows us to call our methods in whatever order we please. Default arguments gives us the ability to specify default values for our arguments. And in case default arguments are tough to invoke by regular means, we can use them in combination with named arguments. In this session, we're going to discuss two methods that are a necessity in learning Scala: AsInstanceOf and AsInstanceOf. Both of these methods are in the superset of all classes called Any. For information on the Any type, please refresh your memory in the Any, AnyVal, AnyRef session earlier in this chapter. Since AsInstanceOf and AsInstanceOf is a method from the type Any, that means that those methods can be used on any object and any primitive. Let's go to the REPL and try this out. We could do 3 AsInstanceOf int. Now these square brackets are what are called a parameterized type, and we'll be discussing that in the next session. If I hit enter, this is going to return a Boolean whether 3 is an instance of int. If I do 3, is this an instance of Boolean? This would say false. I mean, obviously, the number 3 is not an instance of Boolean. If I did is 3, is that an instance of Boolean? Of course, this would be false as well. But if we did 3 is I'm just doing a tab completion here by hitting the tab key. Is this an instance of string? This would return true. But it goes a little deeper than that. If I do string of 3, is this an instance of car sequence? This would also be true. Car sequence is a super type of string. That's why this worked. So therefore, is instance of car sequence returns true for a string and a car sequence. Here's the family tree for string. Any type that makes up your object will return true if it inherits from that type. A string is a car sequence. It's also an AnyRef, and it's also an any. It's worth mentioning that all these types come from Java. And for those coming in from Java, this is going to be a replacement for the instance of keyword. Now, let's go back to the REPL, and let's talk a little bit about casting. Casting is forcibly converting an object from a super type to a more refined type. I know it sounds like a lot of nerd talk, so let's show an example. We know that string, car sequence, AnyRef, and any are all in a linear relationship. Again, let's take a look at that family tree. String, car sequence, AnyRef, and any, they're all in a linear relationship. Assigning a super type to an object is no problem. So let's get started with an example. I'm going to create a file called is and AsInstanceOf. So let's say we start off with val g, and let's make g of a type any, and let's assign this to, all right, kind of a silly one. Any is the super type, and string, if you remember, is a subtype. And therefore, this assignment does not require any cast. We're taking the more broader type, here it is, any, and assigning it to a more refined type. Now, going the other way, assigning an any object to a string will cause issues, and this will not work. G is a reference to type any. H is a type that only refers to strings. We save this, and if we run it, this will cause a type mismatch. Again, we're trying to take something of an any type, which is much broader, and we're trying to shove that into something more refined, the string type, going the opposite way. And because we're assigning that broader type into that refined type, we need to cast. But Scala doesn't have a cast like C, C++, or Java. Our cast is actually a method called AsInstanceOf. So let's give that a try. So I'd like to take G and convert that using AsInstanceOf with a type that we wish to convert to. Let's save this and run it. Okay, success. We didn't have any print line, just knowing that it compiled and ran means that it was successful. The two methods, IsInstanceOf and AsInstanceOf, go hand in hand. It's usually very dangerous to perform an AsInstanceOf on something that you don't know the type of. Therefore, the methods will usually work in combination. I say usually because under most circumstances, you will need to do this. But there may be a time that you are in complete control of a particular situation and you may not need to convert to another type. Let's do an example for that. Let's say I have a method called decide, and decide is bringing in an any. And I'd like to ask the question, so this is a method called decide. It has one method parameter x, which is of a type any. In other words, we can call this method with anything that we'd like. And the implementation for this method is, if x is an instance of int, then what I'd like to do is convert that x to that instance of int. Very much like in our line 2, we took something and converted it into an instance of string. In this case, we want to do essentially a cast to an int and then add 1 to it. Otherwise, we will return -1. Again, this is determining the instance x first before performing the cast. Once we determine that x is an int, we can say, all right, I know it's an int, convert it to an int and add 1. So let's give it a try. Let's do a print line, decide, and if we give it something that is a int, then we will add 1. Otherwise, if we give it something that is not an int, we should end up with a -1. So the answer on this should be a 5 and a -1. Let's run it. Now let's say we didn't write it correctly. Let's go back to our code. I'm going to create another method called decide poorly. In this case, I'm giving decide poorly an any, And I'm going to make a strong assumption that anything that is given to this method is an int. So if we do a print line, decide poorly with a 4, let's run this. That'll work just fine. We're adding 10 to it, we gave it a 4, and what we get back is a 14. That works great. But where things go wrong is if we give it something of a type that is not expected. If we don't do our due diligence, things are going to go really wrong. Get an exception. The exception is called a class cast exception. Java lang string cannot be cast to a Java lang integer. And for those coming from Java, you likely already knew this. And this follows the same rules in Scala. For those who are really paying attention and wondering why I didn't talk about the square brackets again, these are parameterized types on a method, and we'll cover that in the very next section. So in conclusion, IsInstanceOf will return a Boolean whether the object in question is truly an instance of that type or supertype. AsInstanceOf will convert the object to any other type. AsInstanceOf will require that the object is convertible to that type. And any kind of bad call to AsInstanceOf will result in a class cast exception. In this section, we discuss parameterized types on a method. Parameterized types gives us the ability to maintain type safety when calling a method. This keeps us from referring to an object by its supertype. Parameterized types in Java are known as generic types. Parameterized types in C++ are called templates. They're not the same thing. Both C++ and Java have their own rules when dealing with generic programming. In this section, we'll perform generic programming, but we'll do so the Scala way. So let's get started. Let's create a file called parameterized types on methods.scala. And for our simple example, let's say we want to call a method with a Boolean and 2 items, and those items can be anything. So let's get started. I want to create, again, a method called decide. This has 3 parameters, a Boolean, and 2 items that could be anything. And in our first example, we're going to use the any type. This can return an any, and the implementation is. So again, we have a method called decide. It's bringing in a Boolean and bringing in 2 any's and returning an any. If B is the Boolean, so given that Boolean, if the Boolean is true, return X, otherwise return Y. Now we're going to create some print lines. So let's say for the first one, we're going to call decide. If it is true, then return the string of A, otherwise return the string of B. In the second example, we'll have false, therefore 10 will be returned. And in our third example, if it is true, return the character of C, otherwise return the character of D. Now let's go ahead and save this, and let's go ahead and run it to see what happens. Okay, so we are returning a string of A, a number 10, and a C. Let's go back to our code. And that works. It works just fine. Decide takes a Boolean and 2 of any item. Remember, any is the supertype of all objects and primitives. We're also returning an any. Problem is that it sure be nice to maintain that type when invoking the method. What do I mean by that? Well, let's take this line right here and let's bring it over to a REPL to see what I mean. Okay, so I'm bringing in that decide method. It's bringing in a Boolean and 2 of any item. Now, what happens if I call this method? Let's use the characters in this case. This returns a C, but the problem is this is returning an any type. It'd sure be nice to have this return a character type. There's another problem with this. Let's go back to our code and add a few more items. Let's say we wanted to add a method called getNextCharacter, and this receives a character, and the implementation is. Note, we have to add the toChar. Reason is that any JVM language, if you add a number to anything that is smaller than 32 bits, the result is going to be promoted to an int automatically. Character is 16 bits, and since we're adding a 1 to that character, the result is going to be an int. To make sure that it's not going to return an int, I have to call toCharacter to make sure that it is a character. Now, focusing on this method is something that takes in a character and returns a character. Now, if we want to call getNextCharacter, we have to provide it a character. And I'll state that again. We have to provide that a character, the method getNextChar. And there's no going around that. In other words, if I add the following line, in other words, we're doing a print line. We're calling getNextCharacter, which accepts a character, and we're calling it with whatever gets returned from decide. Decide is going to either return a C or a D depending on the Boolean. So let's save this, and let's go ahead and run this to see what happens. We have a type mismatch. Remember, decide is returning any, but what was required was a character. It states so right here. We are expecting a character. Now, we could do a workaround, so let's go ahead and do that workaround. Let's go back to our code. So let's say in the meantime, we cannot do this. What is our workaround? Well, we can create, let's say, a result. And let's say we're going to call our decide method with the values that we tried previously. And call if. And do you know what this is now? If you don't, go back and take a look at the video series for AsInstanceOf and AsInstanceOf. So if this was a character, then what I'd like to do is I would like to do a cast. Remember casting? What we're doing on line 11 is making sure that result is an instance of character. If it is, then we want to cast that into a character. Remember, result is of a type any. That's why we need to do all this. Finally, now that we have this particular result, what we can do is we can call our getNextCharacter with the result. Let's go ahead and save that. And let's go ahead and run it. So the first three items was from our first example, but the D here is what we want. Let's go back to our code, and here's the D. This is the reason why D was printed out. But already I'm kind of sad. This was a lot of work. I had to ask the result whether it was actually a character, and if it was, then I needed to cast that over to something called carResult. carResult could be whatever name I wanted to. It was just a name that I made up. I had to call AsInstanceOf and AsInstanceOf, and then finally get the result that I want. Now, we have parameterized types, and we've used them already. In fact, these brackets right up here are actually parameterized types themselves. This is a method, AsInstanceOf and AsInstanceOf. They're just using parameterized types. Now, it would be nice if we can do a parameterized type on our own method on decide. So let's go up here and let's say we want to convert this decide method to use these parameterized types. That way we're a little bit flexible on the any. So let's change all any's to a parameterized type of t. This will return a t. And before we use these parameterized types, I have to declare up front, in front of the method, that I am using a parameterized type t. Here it is. It's worth highlighting. This is the parameterized type t. This is telling the method I am going to use any type, but whatever it is, keep that type around. And this is the parameterized type. In other words, if you call this with int, it's going to maintain that t is of a type int. Let's save this. And what I'd like to do, let me copy this new method over to the REPL. Let me show you what I mean. Let me call :reset to clear everything out. And I'm going to go ahead and paste the new method onto the REPL. So this is a method called decide. It is parameterized. T could be anything. We're declaring it up front that t is a parameterized type. So let's see how this works. Pretty neat. This is not returning an any. This is returning a double. Now if we try it with something like this, what do you think the answer is for this one? I'm calling decide with a Boolean and a double and a string. This will return an any. In this case, what the type system is going to do is it's going to see a type of double, which is under AnyVal. It's going to see a string, which is under AnyRef. Going to find the common parent. And the common parent in this case is any. Try something a little bit harder. This returns an int. Due to int promotion of the character. Remember, behind the scenes, a character is a number. It is a 16-bit number. and it interacts with an int. Therefore, due to promotion, it is going to be converted to an int. And again, as a reminder, any numerical operation with anything smaller than an int will by default result in that promotion of an int. Anything that involves a long as part of the operation will result in a long. Anything involving a floating point will result in a double. Greatest thing of all this is that now we can call getNextCharacter without any of the AsInstanceOf or the IsInstanceOf calls as we had before. So let's go back to our code. And what I'd like to do is I would like to comment all this out and bring this back. Let's save it. And remember, we converted this to a parameterized method using parameterized types. So let's save it. Let's go back to our command line prompt. Let's run it again. Great. Again, I didn't need to use all the AsInstanceOf or IsInstanceOf. Works out really well. Why does it work? Because the types match. Let's go back to our code. Decide now can return a character. It doesn't have to return an any. We're not forcing it to return an any. This is a huge plus. It makes a huge difference because we're giving it two characters for x and y. That means since that is the same type t, we are returning that type t. And since type t is already established that it is a character, then we are returning a character. No weird type checking, no weird typecasting is necessary. And I think you'll agree, although it takes a little bit more thought and planning, it's a much cleaner solution. So in conclusion, parameterized types help maintain type consistency. Parameterized use brackets as opposed to the greater than or less than characters, as you saw with our examples. Parameterized types are known as generics in Java, templates in C++. The implementation is different in Scala. It's preferred that you use single letters for the parameterized type. In our example, you saw us use a T. You could use A, B, C, D, E, whatever kind of letter you want. You could have full names, although that is outside of Scala convention. In this section, we finally talk about classes. Classes are the templates or blueprints of a construct that encapsulates state and manages behavior. Classes have been around for a long time and in every object-oriented language. Since Scala is half object-oriented language, half functional language, there are naturally classes. So let's see what a class looks like in Scala. Here I am in the editor, and I'm going to create a class called employee, and employee will have a first name of type string and a last name of type string. I'm going to save this into a file called employee.scala. Now for the Java programmers among us, that is it. Well, sort of. We have to add probably a few more things here and there to get what we want, but it isn't too much. In Java, there are all these ceremonial incantations we have to do in order to make this work. Creating getters, creating setters, etc. Whereas in Scala, it is very straightforward and very to the point. Again, for also the Java programmers among us, also notice there is no public. The reason? Everything in Scala is already public. Therefore, the public keyword is not required. How does this look in the JVM? Well, let's compile this. Just make sure I save it. Let me go over to the command line. Here I am in the command line, and I'm going to compile employee.scala. Now let's take a look at the bytecode using a command called javap. This comes from Java. This does not come from Scala itself. Scala C created a class file. In fact, before I even create this, let me just do a directory search. As you can see here, we have an employee.class. So I'm going to invoke javap-p and the name of the class. And this shows what the Java equivalent of the Scala code looks like. If you ever need to see what Scala is doing, javap is an excellent tool. The -p that you see there stands for viewing the private member variables in the equivalent Java code. Take a look at the constructor right between the braces. That's the constructor. It's called a Java constructor. It's called a Java constructor because it happens to have the same name as a class. It's fairly interesting. It has a constructor that takes two strings. But where did we create that constructor? Well, let's go back to our source code and look at that. The constructor happens to be right here. This is the primary constructor. Constructors are quasi-methods that is in charge of setting up the state of the object. Whenever we instantiate the object, it is the constructor that's in charge of setting up that state. As opposed to other programming languages that typically favor an empty constructor as the private constructor, Scala's primary constructor, the one you see here, is big and needs all the information. The reason? Immutability. When Scala programmers change data, they usually get a copy in return. And sometimes copying can come at a price, and that price is memory. In order to avoid excessive copying of objects, we create objects by providing all the information to the class up front. So given this now, let's instantiate a class through this script. I'm going to create a file called employeescript.scala. And in this script, I'm going to instantiate the employee object, and I'm going to instantiate the object with the very first computer programmer. Let me add a print line to make sure I have this correctly, and I will go ahead and save this. Now, let's go ahead and run it. I'm going to invoke Scala, just like I have done in the past with all these scripts that I've done, except this time I'm going to provide a switch called classPath, and I'm going to state that in this directory there's a class that interests me, namely employee.class, that I wish to use in my script. And we get the employee. Now, if you're unfamiliar with JVM programming, this is the default toString. We'll correct this a little bit later. But we get the employee object in return. Now, what I'd like to do next is I'd actually like to get the first name out of this particular employee. Let's give that a try. Let's go back to our code. So inside of the script, I'd like to get the first name. This is an accessor in Scala. It allows me to access the information within the object. Let me go ahead and save this, and let's run it. And we end up with a big stack trace, and this states here that no such method error, employee.firstName does not exist. So let's go back to our code, and first name does not exist. But believe me, this is an accessor in Scala. This is the way we access information. For the Java people, you may be a little bit startled by this. Why am I accessing the field directly? I'm not, nor am I trying to do so. Accessors are not in the same style as in Java, also known as getters. You merely call the method as it has the same name of the member variable. In other words, the method name and the member variable are the same. This is what's called the uniform access principle. The uniform access principle states that variables and parameterless methods should be accessed using the same syntax. In other words, the field and the getter are going to have the same name. Let's go back to our code. So simplifying that uniform access principle, that means you don't know if you're accessing your data directly as a field or from a method. Benefit of that is that you can make changes without adversely changing how people interact with your code. To make this work, we need to add an accessor. And we do this by putting a val in front of the constructor parameter that we need to access. So let's go back to our employee.scala, and in front of the member variable for first name, I'm going to include a val. I'm going to save it and compile it. Now I'm going to run our script. And we get in return Ada. This looks fantastic. So what happened? Well, let's take a look at the bytecode. Remember our bytecode, in order to take a look at our bytecode, we're going to use Java P-P. And our bytecode says, well, you have a private member variable, happens to be final because it is a val, and the name of the private member variable, first name. The name of the method, first name. This is the uniform access principle. The return type for this method happens to be a string. Let's take a look at the employee script. That's why when we access this, we don't know if we're actually calling the method or the private member variable. So this worked out great. Now you could probably imagine what happens when we add a var. So let's give this a try. So for last name, what I'd like to do in this example is make last name a var. Now, let me place a warning here. It's worth emphasizing this again. We particularly don't like vars, but we're just learning right now. So let's go ahead and create the last name as a var. This generates a Scala mutator. So let's go back to our script and mutate the employee. We'll call Ada last name is equal to, and let's give Ada Lovelace her full name. Ada Byron, Countess of Lovelace. This is the way we change our object. So we're changing Ada Lovelace's last name to Byron, Countess of Lovelace. Let's do a print line to see if all this works, and I'm going to print out the last name. Var works as both a read and a write. everything that is writable is also readable. So if you put it as a var, that means not only can you set it, but you could also read it. Let's save this and let's run it. First off, let's compile the code, then let's run the script. We're able to see now that we can change the last name, and we could do that because we listed last name with a var. Let's take a look at the bytecode again. Things have changed though. Let's see what we have. This contains a method, defLastName, which is the method where we get the last name. But defLastName is this method right here, just called lastName, which returns a string. But we also have another method, peculiar one too. This says right here, public void lastName underscore $EQ. This is that equal that we used to set the last name. Let's go back to our code so you can see that. Here it is right here. This is that equal that we're referring to. So this is actually a method called lastName underscore EQ. Let's go back to the command line, and this is what we're actually using. Remember that once the underscore is established, you can add any character that you want. The Scala compiler will just go a little bit further and name your method with an underscore equal, and you can call it without the underscore. So let's go back to our script, and this is the equal that we're referring to. It's very important to note that Scala programmers rarely use var, again because we prefer immutability in all our code. It's very typical for us to use val consistently. So let's go over to the REPL, try something else out. So this is the way that we typically do things. We'd like to have vals for each member variable. If all this seems like a lot of syntax sugar, it is. It may look like it, but this is actually common form. So in conclusion, classes are templates or blueprints. Val creates accessors, methods that will allow us to access the inner state. Var creates mutators and accessors. Mutators allows us to change the inner state. Very important to note, we rarely use var. It's also worth to note that Java P space -P is a great utility to view how Scala compiles to Java. In the last session, we created a class called employee. In that class, we also had accessors and mutators. An accessor is a method to obtain the internal state of an object, and a mutator is a method that can change the internal state of an object. Those forms, though, were unfamiliar to the Java programmer, since the Java programmer deals with what are called getters and setters when it comes to integrating their code into a Java framework. In this session, we're going to talk about creating Java-style accessors and mutators called getters and setters. And when we do so, those getters and setters will coexist with the Scala accessors and mutators that we already have. We start off by looking at an example of a getter and a setter in Java using an example class called person. And here it is. Given a property age of primitive int, the Java Bean convention is that in order to access the property, you provide a getter in the form of getAge, and that is a method down at the bottom. Public int getAge. Internally, we are returning the internal state. We are returning age. For a mutator, it takes the form of setAge with a method parameter of age. Public void setAge, again, method parameter int age. Once we obtain this age via the method parameter, we are going to set that to the internal state, calling this.age and setting that to what comes in from the method parameter. The private access modifier on what's called the member variable, private int age, close to the top of the class declaration, states that direct access to this field cannot be done from the outside of the class. I did say class and not objects, since objects that are created from the class can access each other's private fields and methods. Now, because we love Java and because we are aware that we have to interact with Java frameworks, since Java is so dominant in the enterprise, there is a quick way we can get these creators and setters in Scala. And that is done using an annotation called bean property. The bean property annotation comes from the package scala.beans.beanProperty. And when applied to the property name of the primary constructor, it will create a getter or a setter depending on whether the property is a val or a var. Let's go to the employee.scala file that we created in the last session. Here it is, class employee, val first name of type string, and var last name of type string. The comment here stating that Scala programmers do not like vars in particular, but this is a learning video series, so we will just keep that in there. We will now import the Scala bean property annotation, so that way we don't have to litter our class with fully qualified names of our annotation. Now that we import it, we can apply that annotation on the property that you need a Java style getter and setter for. But let's try this a property at a time by applying it to the first property, first name, and using Java P to view the outcome. All right, so we applied the bean property annotation to the first property, first name, and we're applying it right in front of the val. Now let's compile it. And now let's run Java P space -p on the employee class. We then see that there is a getter for first name in the Java format, and here it is. Also note that the first name property only has a getter. There isn't a method in here called setFirstName. And the reason is, of course, is that the first name property has a val. Let's go back to the source code. Again, this has a val and not a var. And as we know, val means that once it is set, we can no longer change it. So it stands to reason that since we can't change it, there will not be a setter. Now, since we're back in employee Scala, let's add a bean property to the last name property. This time, though, it has a var and not a val. So we should expect that last name will not only have a getter, but a setter. If you want to make this cleaner, you can put a new line inside of the primary constructor. Let's compile it and view the results with Java P. All right, so here we go. This time we have a getter. Here's the getter for last name. Remember, last name was a var and not a val. And this is our getter, and here is our Java setter. Getters when the property is a val, and a setter when the property is a var. So in conclusion, if you need Java style getters and setters, use the annotation Scala bean property. Then you apply the annotation to the property you need a getter and setter for. If applied to a val, you'll get a getter. If applied to a var property, you'll get a setter. In this section, we will discuss constructors in Scala. Constructors are specialized methods that are invoked to construct an object. It is a primary opportunity to set up state. In our session, we will re-emphasize immutability, revisit the primary constructor, and create ancillary constructors that support the primary constructor. So let's get started by reopening our employee class that we created in our previous session. What you see between the parentheses is the primary constructor. When we create an instance of an employee, we give the constructor a first name and a last name. Let's also open up our employee script that we created in our previous session. Here we use the keyword new to instantiate the employee, and we're giving it two items, Ada and Loveless, both strings. The first one is the first name, second one's the last name. And this in turn calls the primary constructor. Now we know that because of immutability, everything must be called in the primary constructor, since creating an object with little or no information in an immutable language will result in excessive copying and memory consumption. So let's change things up. Let's say for our example, we want to add some new data. A title for the employee. Because we made this change, this will affect our script that runs it. Let's open that up again. This line right here will cause an error because we're giving it two items, two strings. Problem is now, because we added the title, we have three items on the primary constructor. Two items being given, and here we have three items. So let's save this, compile it, and prove that we get an error. First, we will compile our employee.scala. Now we will run our script. So we get a no such method error because our script is looking for employee, a constructor that takes two strings, but it does not exist. If we don't want to affect other people's code, we can add another constructor, an ancillary constructor to maintain the interface that others expect. So let's go back to our code and fix it. So I'm going to create a body of the class, and I'm going to create an auxiliary or ancillary constructor. I'm going to start off with the keyword def, and the method name is going to be this. It's going to take two parameters. Given those parameters, I'm now going to defer this call to the primary constructor. I'm going to use the first name that was given over here. I'm going to give it a call to the primary constructor with that first name and that last name. What am I going to do with the title? Well, at this particular moment, I'm going to give it a particular value. And the default value I'll choose is programmer. Again, we start off with what looks like a method named this. This is no method, it's another constructor. We create an employee object with this alternate form. The word this signifies that it is a constructor. This is unlike other object-oriented languages that use the same class name to signify that it is a constructor. Like a method, though, the constructor accepts parameters, and we are accepting a first name and a last name. Once the parameters are obtained, they can be plugged back into the primary constructor by calling this. We'll take those parameters and send them to the primary constructor. Notice, though, that because the primary constructor is the dominant constructor, we have to provide a default value for the title. This entire line is an alternate or ancillary constructor. Notice also that our constructor parameters are a subset of the primary constructor. Ancillary constructors are always going to accept a smaller number of the parameters than that of the primary constructor. As another rule, every ancillary constructor needs to find a way to call the primary constructor. This will look a little bit different than what you're used to in a more mutable language, where the constructor with no parameters will call one of the ancillary constructors with more parameters. This is essentially flipped in Scala. Primary constructor is the one with the most parameters. All others must support either directly by calling the primary constructor or indirectly by calling the primary constructor from one of the other ancillary constructors. This is the typical form in Scala. Now, when we compile the employee.scala file and run the script, this will now work. So let's go ahead and write this, compile, and run the script. Great. Now, let's go to our script, because what I'd like to see is I'd like to see what the title for Ada Lovelace is going to be. So I'd like to do a print line. Again, I did not explicitly state her title. I'll save it. Now I'll go to the command line. By default, she has the title called programmer. Now it's worth noting that the constructor can be written differently. What we did is the common way. Let's go back to our code. I'll go ahead and make a note here. This is the typical form. We could write other forms for these constructors. For example, let's go ahead and comment this out and rewrite it in a different form. Nearly the same initially, in fact, very much the same initially, except this time we can call it with a block. This isn't too out of the ordinary. Let's save it and let's give it a try once again. Works out great. Let's go back to the code. Now, what's great about the block is that if you have other statements and you want to include some side effects, let's say printing to the screen or setting state, you could do so after the call to this, but you do need the block first. Anything that is a multi-line would require a block. So let's try another form, this time with a side effect. So here I'll state a typical form with side effect. And in this example, I'm going to place a semicolon. Anytime there's a multi-line in the same line, I could use a semicolon, or I can just do my side effect here without the semicolon. Okay, now it's worth warning that a call to this needs to be done first. So let's try this code first, and then what we're going to do is we'll flip these lines next. So first off, let's go ahead and save that. I'm going to go over here and just check to make sure that everything will work. Here it is. There's the compilation, and let's go ahead and run the script. So everything works great, and also we have this side effect. So as I mentioned previously, this call needs to be the first call if you're going to have other lines within that constructor. Let's go back. Now, what if this was not the first line and the call to this was on the second line? The compiler will not allow this. So let's go back to our command line. This will say error, this expected but unidentifier was found. So let's revert back to our correct state. Now, in none of these circumstances do you even require an equal sign. I prefer it because it is convention. So the first couple of atypical examples, we can get rid of the equal sign. So let's just copy and paste some of these examples and try them in turn. Let's try this one, and this will be the atypical form without equals. Let's see how this works. Saved it, compile it, running the script, everything works great. Let's go back to our code. Now let's try the multi-line with the side effect. This time, though, without an equals. Save the file, compile, and run the script. As you can see, everything works great. Now, I'm a sucker for convention. I don't particularly like performing any side effects in the constructor. I'm not going to say I'm never going to do that. There may be a circumstance where I would, but something like that is typically a code smell. So what I'm going to do is I'm just going to go back to the correct form. It is again worth reemphasizing a few points. One is that the line here, this one that I'm showing you, is the typical form, and this is what you'll mostly see from Java programs throughout the internet. The other thing is that side effects that you see here are many times frowned upon. We have two different examples with side effects. So that's something that you won't see very much. I did these examples just to show you the language flexibility, purely academic. Also, another thing to mention is that when multiple ancillary constructors are in use, you can chain multiple constructors until the primary constructor is called. In other words, if you have a primary constructor and another constructor will call it A and another constructor will call it B, you could have B call A and then A call the primary constructor. Although we can force an example here, we have an excellent example for you when we cover options in a few more sections. So in conclusion, ancillary constructors look like methods named this. Primary constructors are meant to ask all the information up front. Ancillary constructors, once called, need to find a way to the primary constructor, either directly or indirectly. The call to another constructor uses a method call to this. The call to another constructor needs to be the first line within the constructor body, otherwise you'll get a compilation error. In this episode, we take the knowledge of what we learned about default and named arguments and use them in constructors. In the session, Default and Named Arguments, we learned about default and named arguments in methods. This session is to inform you that the same rules used for methods can also be applied to constructors. Let's take a look at our employee class that we've been working on for the last few sessions. We have two constructors. The first one is the primary constructor. It takes a first name, last name, and title. The second constructor is one that takes a first name and a last name, but it feeds it back up to the primary constructor with a default string of programmer for the title. Let's go to our employee script, and let's start off by invoking one of the constructors using named parameters in the employee script. So I want to instantiate a new employee, but this time I want to specify my own order, so I'm going to use named arguments. So I'm creating Dennis Ritchie, famous for the C programming language, and we want to call our constructor with a name parameter. Again, we want to decide the order. We have the power. So I'm going to go ahead and save this, and before I continue on, let's add some print lines to this. And let's make sure that we have the correct values by doing a couple of print lines. We saved it. Now let's run our script. We do not need to compile employee.scala since we've made no changes to it. Great. First name is Dennis, last name is Ritchie. That looks fantastic. So again, named parameters can be used for methods and constructors. What about default parameters? Remember from the previous session named in default arguments, we use default arguments to set up a default value so that the invocation of that methods parameter, remember we were talking about methods at the time, that could be optional because we provided a default value to that particular argument or parameter, however you like to call it. So let's try doing this for a constructor. So let's go back to our code. And what I'd like to do now is for the title, I would like to provide this with a default title of programmer. Well, this makes things interesting, doesn't it? So what does this mean? This means that the title has a default in case we don't call it. And it also means that we don't need our ancillary constructor. In fact, we don't need any other constructor. Very interesting. Now let's save this. Compile employee Scala, and then run our script. This works. With Scala, you have a lot of different choices. You could either use a constructor or you could use a default parameter to achieve the same effect. So in conclusion, named arguments allows us to invoke our constructor by constructor or the parameter names. Named arguments also allows us to call our constructors in whatever order we please. Default arguments allows us to specify default values for our arguments, but this time in constructors. We did it before in methods, we did it now with constructors. In case default arguments are tough to invoke by any regular means, you can use them in combination with named arguments. In this session, we'll talk about methods within the confines of a class. And we will also address an issue of a bug that may occur when running a script, and we'll talk to you about how to overcome that issue. Now, we've discussed methods, how they work, but we've done it in isolation. So we're going to bring those into a class. And as you may have already surmised, this works inside of a class and works to add functionality to that class. So let's get started with our employee.scala file that we've been working on for the last few sessions. And this time what I'd like to do is add a method called fullName that returns the concatenation of our first name and our last name of our employee. So let's go back to our code and see where we left off. So here's our code, and what I'd like to do is add another method onto here. Well, this would be our first method, the rest have been commented out, but we like to add a method called fullName. And the return value, we don't have any parameters, so this is just something that we purely return. Let's use string interpolation, and we'd like to bring in the first name and the last name. Great. So here's our method. Now let's go to our employee script and invoke our method. So here's our employee script from what we had last time, and what I'd like to do is add a couple of print lines. One, I'd like to see Ada Lovelace's full name, and I would like to see Dennis Ritchie's full name as well. We're going to save that file. So we saved our employee, we're saving our employee script. Now let's compile employee Scala and let's run the script. This looks great. Our last two lines show the full name. One is Ada Byron, Countess of Lovelace. The reason why it says Countess of Lovelace is because we've changed the last name. And then finally we have Dennis Ritchie. Worked out great. The method inside of the class is in a support role for the class and its member values and variables. Now let's go back to our code. Let's try something else. Now, within employee, we have this var. Now, if you take a look at my line 26, it says right down there, warning, Scala programmers do not like vars. We particularly don't like vars because every time there's a var, there's something mutable going on or changeable. Now, let's say we want to change this var, and let's go ahead and do it now, to a val. Question is now, since this is val and unchangeable, how do we update the last name member value when these member values are unchangeable? Well, the answer to that will be a method. So let's create a method called changeLastName. I'm going to bring in ln. This is of a type string. This is a method parameter. And what we're going to do is we are going to return a new employee object. This employee object will bring in a first name. But what we're going to do for the last name is we're going to take this ln and plug it into here. The first name that we created happened to be the already established first name that is in our object as a predefined state. Then we will add last name. And this too is also predefined from what is within the object. So again, we're taking a string and we're using it in the construction of a new employee object. The key to immutability is never change the original state, but to make a copy. And what we're doing here is we are returning a new employee, which is a copy, but except this time with our copy, the last name has changed. Now let's go to our script and update that. Now right up here on my line 4, I am calling ada.lastName is equal to the new string. But what I'd like to do is I would like to change this to the new method that we just created called changeLastName. The thing about this call though is we are returning an object. We are returning an employee from changeLastName. So we need to assign this to a new value. Preferably a val, of course, because vals are rarely ever changed. But because we did this, we have to change every other reference that happens afterwards. So what I'd like to do is I'd like to change Ada, period, to new Ada, which is the name of the new reference, period. So we'll change this, this, and this. Now what else I'd like to do is add another print line here, Ada.fullName, because Ada is the original reference. So what we should be expecting here is that the third from the bottom of the line should just be Ada Lovelace. The second to the bottom line should be Byron, Countess of Lovelace. And then finally, as the last line, that should just say Dennis Ritchie. So we saved our script. Let's recompile and let's run our script. There's our recompilation. Now let's run our script. So what we end up here with, unfortunately, is a bug. I'm fairly confident what we did will actually work. And this states right here that changeLastName is not a member of employee. But we did save our file, and so I'm pretty sure that this is going to work. Now what the problem is scripts use something called FSC, known as the fast compiler. FSC is a compiler daemon, in other words, something that runs in the background. It's also a cache that caches compiled code, so it doesn't need to recompile. This is actually a wonderful thing, particularly when running scripts where we don't always have to recompile code. The issue is that its cache sometimes isn't fast enough to be notified of these changes every time we make some new code. I think this has something to do with the latest version, 2.11.7, although I've seen this in 2.11.5. In a future session, we'll be using something called an object to run our code. But right now, we're just dealing with scripts. So I still do consider this a bug at this time. But our workaround is I would like to run the script using something called the dash and C switch. The dash and C switch prevents Scala from accessing classes from the fast compiler cache and will use the class files directly. So what I'd like to do is run Scala, this time NC, again, don't use the fast compiler, and let's run our employee script. So we are using the classes from the class path directly, and the bottom three state Ada Lovelace, Ada Byron, Countess of Lovelace, and Dennis Ritchie. Exactly what we were expecting. This is really neat. Also note, again, that the original Ada contains the original information, while the new Ada contains the newer information. Now, what's really great about immutability and creating copies every time we make a change is that we get an automatic design pattern from the original gang of 4 design patterns called the memento pattern. We get to see what happened in the past because we have a copy of what happened in the past. Not only that, but immutability is safe for concurrency across multiple threads since there's no need to synchronize change in states, particularly in processors. Now, let's go back to our code. The change last name method is a bit inelegant, and we'd like to go a little further and create one method that can update our object for us in an immutable way. But this will use default and name parameters to implement. So let's go back to our code and get started. All right, so here's our change last name method. So what I'd like to do is change this around and create a one-stop shop for immutability by making something called a copy method. So our change last name is no longer there, and we're going to create a brand new method in its stead, and this will be called copy. And what we're going to do is we're going to bring in all the parameters from our primary constructor. What we're going to do is we're going to use default parameters here. So first name is going to retain the state that we already have from within the object. And we're going to make a call to this. This just means within the object itself, give me the state of first name, which is a property internal to this object. For last name, we're going to bring the already established last name. And for title, we'll go ahead and bring in the already established title. And what we're going to return is a new employee object. We're using the same methodology as we did before. And what we're going to do is we're going to plug in the first name, the last name, and the title. Let's clean this code up a bit. That way we get to see how everything's working. We can create a block here if we'd like, just to make things a little bit cleaner. All right. So there's our copy. Again, we're bringing in a first name. This will use a default parameter. This will use the state that's already been set. Last name, the default parameter will be the last name that's already set. And title will have the property that's already been set within our object. And what we get in return is a new object, a new employee with those new fields. So let's try it out. I'm going to go ahead and save employee Scala, and let's go to our employee script. And this time we'd like to use name parameters to specify which parameter it is we wish to copy. So here we are in our employee script, but on line 4, change last name does not exist anymore. So let's get rid of it. And what I'd like to do is I'd like to invoke the method copy. But we have to use the name parameter now. And what we're going to do is we're going to state that the thing we wish to change will be the last name. So I'm going to change this to state last name is equal to Byron, Countess of Lovelace. Now let's compile our employee Scala and let's run employee script, of course with the dash and C flag, because we don't want it to use the fast compiler anymore. And now let's run our script. Great. Remember, we have to do the dash and C just to avoid the fast compiler issue we were having earlier. But there we go. That looks great. We have immutability and we have our flexibility. So in conclusion, methods are used in classes and they have access to the internal state. Methods can also use default and name parameters for better functionality, and we did so with that copy method. Also, when running a script, we talked a little bit about the fast compiler, what it does. Again, nothing wrong with it in particular. We're just moving a little bit too fast currently. And if we want to avoid using the fast compiler, we can run our script using a switch called dash and C. In this section, we introduce preconditions to ensure that no one will give our class any information that will affect our internal state. Let's go to our employee Scala, the same one we've been working on for the last few sessions. And the problem currently right now, well, let's go to our code, check it out. it is too permissive. Users of our code can actually provide an empty string if they feel like it for our first name, for our last name, and for our title. If we want to go on the defensive, we can do so with a method, and this is actually a method called require. So let's put some requires in for the first name, last name, and title. So here's the first one, require. Next part has to be a Boolean, or something that evaluates to a Boolean. As part of my evaluation, I want to ensure that first name is non-empty. But if this condition is not met, a message will be displayed. Let's try that again for last name. And in this case, last name cannot be empty. And we also want to make sure that the title cannot be empty. So we have 3 requires. Now there's something peculiar about the placement. The first time you look at this, it's going to look a little bit weird. These lines are a part of the primary constructor. They're not inside of any other method. This entire space that you see here is invoked when we call the primary constructor. It is essentially the primary constructor space. Now these require statements all require that the entries of first name, last name, and title are not empty. And to reemphasize, this needs to evaluate to a Boolean. That defines whether a certain condition has been met. Second parameter is going to be the message, and that's the one that would be generated if the condition is not met on the first parameter. Now let's try it with some bad code in the employee script.scala. Let's save this and let's go over to our script. Now what I'd like to do is create an employee, and we're going to create an employee called Bono with no last name. His stage name has no last name, and his title will be singer. So let's save this and run it, and let's see what happens. Again, last name is going to be the empty string. And now let's run our code. I will be using NC just in case there are any bugs, and we had referred to this in our previous session. This way we don't have our classes go into the fast compiler. This will just use the classes that are already in our class path. So I'd like to run employee script.scala, and let's take a look at the results. This is going to produce a stack trace, and if we scroll a little bit up, this is going to state right here, legal argument exception. Requirement failed. This is the thing that we just did with our require. Last name cannot be empty. Now, personally, I would like to keep this file around, and I'm talking about the script. I'd like to keep it around for posterity, and would hate for this exception to keep hanging around and busting up our code. So let's wrap it up in a try-catch block. That way our program runs, and we are able to tell what the reason is for this program failing. So let's go back to our code. And since we know Bono is going to cause trouble, let's surround him with a try-catch block. Here's the try, here's the block, and I'm going to call catch. Now what's going to be different in Scala is that I'm not going to declare the exception here, but inside of the block right after catch. Now a try-catch block, for those who are unfamiliar with them, is like a bomb container system that the bomb disposal technicians use to either defuse or detonate the bomb. If something ever happens, then this reinforced barrel will take up all of the blast. Same type of situation here. We know that when we instantiate the employee on line 18, this can cause an issue. So what's going to happen is the try-catch block is going to catch this particular exception. And since we're able to handle the exception, we can safely continue with our program. All right, now within here, I am going to add a case and a value name, IAE, followed by the type. What kind of type am I expecting? And the type is going to be an illegal argument exception. Next, I'm going to use the implies operator, or the rocket operator. What I'm going to do with this is I'm going to print line whatever the message is from this exception. So let's save it and let's run the script to see what happens. Great. Our program runs successfully, and we have a requirement failed message. Last name cannot be empty. We're able to handle the exception. Let's go back to our code. Now the try-catch block looks slightly different from Java. In Scala, you don't have the exception type and the assigned variable on the same line. The catch keyword stands on its own, and here it is. Inside the catch block, and we're talking about this right over here, we will use a little bit of what's called pattern matching. Pattern matching allows us to match the data with a match first policy based on either the type, which is what we're doing here, we're matching on the type, illegal argument exception, or parts that compose a particular object. If the IAE that you see here is of the type illegal argument exception, then we're going to proceed with what is after the rocket operator. If it isn't the right exception, then the exception remains unhandled and it will bubble up to the console error panel or website error page. Notice that after we match on the exception, we assign the exception to the value IAE, and here it is. Once this assignment is made after the rocket operator, we can refer to it, and we can call methods that are a part of its object. This is a good thing. Now, as a best practice, exceptions should never be hidden and should appear if something is wrong. Otherwise, you'll never know how to fix it. So what we're doing here is not really a best pattern. All we're doing is taking this exception and displaying the message on the system out. But we're only doing this for learning. It also needs to be said that all exceptions in Scala are runtime exceptions. There are no checked exceptions. Checked exceptions are from Java. They are a kind of exception where the caller of the method is forced to handle the exception at compile time. We don't need to worry about that in Scala since they are all runtime exceptions. If an exception happens, you have the option to deal with the exception, or not. You could just let it bubble up to the top of the call stack. So now let's run this. Everything looks good. Now, one thing we could do is we can add a finally block. The finally block is optional, and this is going to run regardless of whether an exception is thrown or not. It's used to clean up resources and perform other chores that you may have. So, as an example, let's just do a print line here stating that we are continuing with our program. Now let's give it a try, no pun intended, compiling our employee and running our script. Okay, as we see here, the last message states we are continuing along with our program. This is because the finally block kicked in. Now require is just a nice way to handle preconditions without an if statement and creating an exception for ourselves. But let's write one anyway, just so that way we get a flavor of what we would need to do. Let's say we have another requirement that we don't want anyone giving themselves a title that contains the words senior or junior. Let's go back to our employee.scala. And in the following line, I'd like to add if the title contains senior or if the title contains junior, then what we would like to do, and I'm just putting this on a new line just for aesthetic purposes, throw a new illegal argument exception. And we'll state here title cannot contain junior or senior. All right, so we'll go ahead and save this. And this is how we do a manual precondition check. Throw will alert the caller that something bad has happened. Now, there are many kinds of exceptions out there, but typically these exceptions, take a look over here, when you look up a pre-existing exception that you wish to use, they'll typically have a class name that ends in the word exception. Find the right one that fits your scenario whenever you need to alert others of a problem within your code. Now let's create a bad entry in our employee script with the title of junior or senior in that title. So we'll save this. Let's go over to our script. Now in our script, let's create someone else. And what I'd like to do, let's just go ahead and make a copy of that. And instead of Bono, let's use Linus Torvalds. And this time, Linus Torvalds will be not a senior C programmer. I am also expecting an illegal argument exception. I don't want this employee script to fail, so I'm going to put in a try catch block, and I'll have this finally here to prove that we're able to continue along with our program. So we went ahead and saved this. Now let's go ahead and compile our employee Scala. Then we will run our script. Works fine. So we see that title cannot contain junior or senior, and we're able to continue along with our program. Now we handle it in a way that was verbose, and again, I prefer to use the require. But this last example that we did just gets a point across as to what require does. Plus, we're able to dabble in throwing our own exception. Let's go back to the code and take a look at that. So here's where we do our try catch, and here is where we throw our exception. Now, what about null? So in this scenario, it's very well feasible that first name, last name, and title could be null. And I'm going to leave this up to you. It's certainly up to you whether or not you want to check for null. If you want to be aggressive, and again, there's nothing wrong with that, to make your class airtight, you can certainly check for nulls. I will say this, seasoned Scala developers will rarely use null, if at all. So you may not have to worry about it. Now, seasoned Scala developers will have to worry about null if this particular class is going to be interrupt with Java. In other words, it's going to be working with some pre-existing Java code. Then there's also the other situation where novice Scala programmers, particularly from languages that use null consistently, will likely use null the first few times they use it in Scala. So I guess the answer for this is going to be know your audience, and I'll let you make that call. So in conclusion, require checks for quality of parameters of either a method or a constructor. Require will throw an illegal argument exception if the requirement is not met. Try catch uses pattern matching to determine if a particular exception is thrown. And exceptions are thrown with the keyword throw, and of course an exception object. In this session, we discussed subclassing. Scala, being a true object-oriented language, allows one class to inherit behaviors and state from another parent class. We can perform subclassing in Scala with the same ease as Java, but with a twist. So let's get started. We want to go back to our employee.scala file. Let's go ahead and make some changes to that. So here we are in the employee.scala file. And to start things off, I'd like to create another class called department. To keep things simple for now, in department, I would just like to have a name. And let's add a few lines here. I'm going to create a department. This will only have one attribute, a name. Now this isn't the class we'll be subclassing. Our subclass will come in with a new class called manager. So let's create that manager class. Now manager is going to have the same attributes as the class that it is inheriting from. And we're choosing to inherit this from the employee class. So we're going to have the first name, the last name, title. This is new, the department. That's what's going to differentiate the manager from the employee. Next, the extends keyword. This is what's going to tell this class to inherit behaviors and state from a parent class. Then finally, employee. And what we're going to do here is we're going to select the attributes that comes into manager that is handled by the superclass. So first name, last name, and title are all handled by the employee superclass. Department, on the other hand, is not. Now, manager is distinct from an employee because it has this department. But a manager is still an employee. A manager also has a first name, last name, and title just like the employee. And the department, since it is distinct to the manager, will likely have a val in front of it. Now, we don't have to have a val in it. This is just so that way we can get an accessor for this department. But if we just wanted to inject this value in and not have an accessor for it, we could just remove the val. We could also have a var, but as stated before, we don't particularly like var. So I'm going to add a val in here and state right here that this val, since the department is part of a manager, we want an accessor from this particular department. Now there are no vals in front of first name, last name, or title because they are forwarded over to the employee superclass via the extends keyword. The class name after the extends shows which class we are subclassing from, and in this case that's going to be the employee. There is one very important rule when subclassing. When subclassing, it is important that the subclass has is a relationship with the parent class. In our example, is a manager an employee? The answer to that is yes, therefore that works. Many who are unfamiliar with object-oriented programming and design may want to reverse that relationship. The problem is that it doesn't adhere to this is a relationship policy. Is an employee a manager? Well, not all of them, so therefore it does not adhere to the is a relationship policy. Be very worried about extending from classes like manager. And I'm not talking about the manager we're creating here. We're talking about the big manager classes that some companies tend to create that encompasses every kind of business logic that the business does. Another violation would be a class called context. Context could be anything. When you're using these broad terms and you're extending from these classes that are too broad, or even creating classes with those names that are going to encompass just about everything, you're likely modeling your application incorrectly. So think about your design. Now, let's try this out inside of our employee script. Let's add a few lines here so we can see what we're doing. Now, I'm going to start things off with a department, and this is the mathematics department. Since department has one attribute called a name, we're just going to provide that with the name here. Next, I'm going to create a manager, and it'll be none other than Alan Turing, mathematician and logician. And then finally, we're going to give him a department. So we're going to take this reference and plug it into the constructor. Now to test things out, let's try a print line. And what I'd like to do is take Alan, take his department. Remember, we created that val under department, so that way we could do something like this and then get the department name. So we went ahead and saved this. Let's go ahead and compile employee Scala and then run the script. So we're going to compile. Now we're going to run. Again, I'm going to use NC. That way we don't use the fast compiler in our example. Here's the name of the department. Pretty nifty. We can create managers now. What we could also do is assign a manager object to an employee reference. So let's go back to our employee script and play around with some of these references. And we'll assign Alan Turing as an employee. Now in this case right here, what I'd like to do is I would like to create another reference. So this Alan right up here has a reference of manager implicitly because there is type inferencing going along, so we didn't have to declare that explicitly. But let's say we're going to declare that explicitly. And let's create another reference called Alan Employee. And Alan Employee is going to be an employee reference. Alan's job, the reference I'm talking about right up here, is to point to manager objects. Alan Employee's job as a pointer is going to point to employee objects. And what that's going to point to is the same reference as Alan. Now what we can do is let's do some print lines. I'd like to ask Ada what her first name is, because this is an attribute of employees. I could also ask new Ada what her name is. I could also ask Dennis what his name is. I could also ask Alan what is his name. And finally, I could also ask Alan, as an employee reference, what his first name is. So let me save all this. So I have 5 lines here. I'm just asking every employee object I created, whether it is a manager or an employee, what their first name is. So let's go over to the terminal and give this a try. Great. So we have Ada. This one is the first Ada reference. This is the new Ada reference. Here's Dennis, and here's Alan. One, because we are using the manager reference, and the other one, we're using the employee reference. Now let's change things up. What I'd like to do is ask Alan, let's try Alan Employee this time, what his department and name is. Remember, Alan Employee is an employee reference, so let's see what happens when we call this. Now we know that the object itself has a department, but the reference is an employee reference. So we're not going to be able to ask this question. And this will state right here, value department is not a member of employee. Remember, Alan Employee is an employee reference. Yes, it's pointing to a manager object, but the reference is an employee, so this is not valid. Let's go back to our code and fix that. Let's do a sanity run. Everything works. Now let's go back to the code. Now what we're doing here is something called polymorphism, the ability to assign an object to any of its hierarchical supertypes. The type of polymorphism also applies to methods. So let's try some method polymorphism. And we're going to add a method to the employee script to give it a try. And the method I want to create is extract first name. And this method will only accept employees. But this will return a string. The implementation, the.firstname. Now we could let type inference take care of this part right here. This will still work. Now let's add a few items. We want to extract the first name for Ada, for Dennis, and for Alan. The first 2 are employee objects. The third one is a manager. So let's go ahead and save this. And now let's run it. There it is. We're able to obtain the first name because the method accepts employees, and every employee has a first name, whether it is a manager or whether it is an employee. Now, something kind of weird is happening to our employee.scala. Let's go back to our employee.scala. We have a class here, we have a class here, and we have a class right up here. We have 3 classes in one file. Now, for the Java programmer, that is really weird. What did we just do? We have multiple classes in the same file. So no longer, especially for the Java programmer, for you, no longer do you have to have one class per one file. Nor does it have to be the same name as the file. And since we don't have to hold to any of these rules, let's rename our employee.scala file to models.scala. Models being nouns. So let's head over to the terminal. So I would like to move employee.scala to models.scala. Now what I'd like to do, let's remove all the class files that are in here. And this is what it looks like. I have models.scala now because we renamed that employee.scala to models.scala. And then we have our employee script. Now I'd like to compile models.scala. And let's do an ls here. Take a look at the directory. As you see here, there are a lot of class files and supporting class files. And even though we had an employee class, a department class, and a manager class inside the models, it was able to detect those and then create those classes whenever we compiled. Now when we run this, it works out just the same. Class files are class files. This flexibility, when used judiciously, can save the developer a good amount of time from file haggling. You no longer have to create the one class per one file. Some of you may view this as more difficult since it is no longer obvious that classes are in a file just by looking at the file name. I'll let you form your own opinions whether you consider this a good thing or a bad thing. So in conclusion, extends is a keyword used to subclass from another class. Any new attributes typically will have a val or var, or you could leave them blank if you wish not to expose the property. But all properties that come from the superclass are sent to the superclass's constructor. Any inheritance from the superclass must have a is-a relationship. All subclasses are polymorphic, either by assignment or method call, and you can have multiple classes in one file. In this session, we'll be covering how to override methods from a superclass. Overriding is a necessary procedure to redefine a method from a superclass with a refined implementation that fits your subclass's goal. For this session, we'll keep it simple and override our full name method from employee and do it inside of manager. We'll also override copy, and we'll also continue to use overriding in our next sessions when we perform equals, hashCode, and toString implementations. In any object-oriented programming language, a method override allows a subclass to provide a detailed implementation of a method that is already provided by one of the parent classes. Given that we have a method called fullName in employee, we could override fullName to give it a different implementation in manager, one that reflects a more apt fullName. In Scala, as in Java, an override must have the same exact signature. To get started, let's go over to models.scala and override the fullName method in the manager class. And for example, let's make that fullName return something different: the first name, the last name, and the department for which they are manager. Here we are at models.scala, and we have our case class department that we had last time, and we also have our manager class that brings in a first name, last name, title, and a department, which extends an employee that will take that first name, last name, and title from manager, but department has a val, so this is a property that belongs to a manager. What I'd like to do is override fullName, and on my line 31 here, it shows that def fullName is equal to the first name and last name. I wanted to add a little bit to this and create a different implementation for fullName. Now within here, I'd like to override the fullName and give it a different implementation. Now, one thing you'll notice with our addition is that there's a new keyword called override. In Java, this is an annotation, and it's used as a safety net on whether a method is indeed overriding a method from a superclass. Remember, an overridden method has to have the same signature as the parent class. And this keyword, or in Java, the annotation will ask the compiler to please check and make sure that we're following all the rules. In Java, it uses an annotation, and that annotation is optional. Unlike in Scala, which is mandatory, the override that you see here on my line 43 is actually a keyword, a part of the language. Not only does it check for being exactly an overridden method at compile time by checking the signature, it's also a way that we could explicitly state that our intent here is to override. Now, let's go to employee script and try out our full names once again. And within there, let's print out the full name for some of our managers. Okay, here we are under employee script, and we've had this from our previous sessions. What I'm going to do is I'm going to copy these three right here, which print out the full name for Ada, new Ada, and Dennis. I'm going to go down here to the bottom and paste them right in here. So I have Ada.fullName, new Ada.fullName, and Dennis.fullName. And I'd like to add a couple more. Now, before I add those couple, let's refresh right up here. I have Alan, which is pointing to a manager, and this is pointing to a new manager that has the first name of Alan, last name of Turing, title of mathematician, logician, and is a part of the mathematics department. And on my line 37 here, I have another reference called Alan employee, but this points to employees, and this is legitimate because as an employee pointer, we can point to a manager. A manager is an employee, so this is okay. Now at the bottom, I'd like to add a couple of print lines. Question is, what are the bottom two going to be? That's an interesting question. Well, I'm going to go ahead and save that. And let's go over to the command line and give it a try. Here we are, the command line. First, let's compile models.scala. And now I want to run this script. Let's avoid any caching by using -NC. Very interesting. The last two are going to show Alan Turing, mathematics manager. And remember, mathematics is the department that Alan Turing happens to be a manager of. Now, we see that the implementation is different based on type. Last five we're actually looking at, Ada Lovelace, Ada Byron, Countess of Lovelace, and Dennis Ritchie are all employees, but Alan Turing is a manager. And even though the second to the last one is pointing to the manager and the last one's pointing to employee, the references that they're pointing to don't matter. What matters is the concrete implementation for each object. You'll notice that interface-wise, the last five all have a method called fullName that looks and feels the same. And notice the strange twist at the end. From our last session, we called Alan employee and noticed that we couldn't call department because we had an employee reference, not a manager reference. Now this time, since both of them have full name for both the employee and the manager, the result is what we're looking at is the implementation of a manager in the last two, not that of an employee. This should make us all at ease that it doesn't matter what reference we're using. We don't care if we're pointing using an employee reference or a manager reference. What matters is the implementation of the object where this was created. Since Alan Turing's a manager, when we call for his title, it's going to be his first name, his last name, and the department that he is a manager for. Now all this is method overriding. We'll be using it extensively in the next few sessions when we discuss equals, toString, and hashCode. Now we could also override the copy method. Let's give that a try. Here we are inside of models.scala, and what I'd like to do is override copy that I have here. So what I'm going to do is I'm just going to go ahead and copy this and save some time. Before I continue, a few things I need to change. First off, this is an override. The arguments need to stay the same. This time, though, I'm going to be creating a manager, not an employee. And because it's a manager, I'm going to give it a department. Now, a true copy would allow me to include my own department right after title, right up here. But by doing that, this is no longer an override, but an overload. That's going to change things a bit, so let's do things a little bit at a time. And again, we're only talking about overriding, not overloading. The moment we add a department to this, it's going to change things around. So let's stick with the override first. And what I'd like to do is let's go back to the employee script and change Alan Turing's title and see if the copy works. Here we are back at employee script.scala. What I'd like to do is add the following. Let's give him a fun title. I'm going to take Alan, change the title around. This will be set to Alan New Job. If all goes well, the last line from our output should state that Alan Turing is a supreme encryption specialist. Let's go to the command line and give it a try. Here we are at the command line. So I would like to compile models.scala. And now let's run the script. Great, there it is. The copy worked. For this reference Alan New Job, if we call the title on it, this returns Supreme Encryption Specialist. We could see that since Alan is of a type manager, the copy implementation of manager is behind the result. Great. Now, you may have noticed a peculiar problem, and we've stated this before. There is no department in our copy. So to round this lesson out correctly, let's change this from an override to an overload and talk about the difference. And this time I'm going to add a department. And if you remember from the last chapter, an overload is where the method name is the same, but the parameters, possibly the return type, can be different. And since we are adding that department, that is a significant change to make this an overloaded method instead of an override. First off, we need to get rid of the override keyword. Let's do so and change things up. Let's head back to our code. Okay, here we are back at manager. Few things that we like to change. Well, first off, let's go ahead and get rid of override. This is department, not manager, so we are going to add a department here, and this will be the same as this dot department. Now within here, we don't need department toys. That was just a default filler because we were not accepting department before. And this time we will call department. That should do it. It's not going to work, but that should do it. Let's go ahead and save it and attempt to compile. This states right here that there's an error in class manager. Multiple overloaded alternatives of method copy define default arguments. I add this example as a warning that shows currently the fragility when it comes to overloading methods from a superclass. That uses default parameters. And again, that uses default parameters. Overloading is still okay to do in Scala, except when it comes to default parameters. It shouldn't come up frequently, and we also hope that the language authors, as clever as they are to find some way to address this particular corner case, I just presented this as something to look out for. So in conclusion, override keyword is mandatory in Scala, and it's not an optional annotation like it is in Java. So if you are truly overriding a method, you have to use the override keyword. Overridden methods must look the same as the method that they are overriding from the superclass. Overridden methods are created to change the implementation for a subclass. And regardless of reference, the correct overridden method will be called. And again, just as an added warning, don't forget that overloading method is where the superclass's method contains default arguments. Those can cause issues. In this session, we discuss equals, hashcode, and toString in an object. Every object-oriented language has logic to determine if two objects, or models, if you'd like to call them that, are equal to one another. We must also create a number to efficiently store our object in certain collections, like hashset or hashmap. These are called hashcodes. We also need a string representation for our object, so that it's not so cryptic when we place it on a system out. What we equate, create hashes, and make string representations for is referred to as business logic in the domain models. Equals, hashcode, and toString are in the AnyRef class, and it is up to us to override these methods in our models to give it something with meaning. We start with equals. In order to determine if two objects are indeed equal to one another, we must override the equals method. Let's start with that. First off, let's go to our employee script. We start off with Ada and new Ada. Ada has Ada Lovelace. New Ada we made a copy of by changing the last name to Byron, Countess of Lovelace. So what I'd like to do is I'd like to create a reference called another Ada that is going to have the same values as new Ada. Now remember, both of these have a title of programmer by default. So let's go down to the bottom of the file. And what I'd like to do is create another Ada. Okay, so here we've created the employee. Let's go to the top to make sure that it's all correct. First name is Ada. Second part, last name is Byron, Countess of Lovelace. Then finally, programmer. And here it is. So we have another Ada. And now I would like to ask, is new Ada equivalent to another Ada? Given the business logic, given that the first names are equal, the last names are equal, and the titles are equal. So let's go ahead and save this. Go to our command line, compile models.scala, and run employee script. Our script runs well, but at the end right here, this says false. Now the equals method that we call determines the equality of the business logic between two objects. Let's go back to our code. So this rendered false. This should be true because all the elements are the same, or we deem that it should be the same. First name, last name, and title, since they're all equal, I believe, and maybe you do as well, that they should be the same. But it isn't. And that's because we did not program our employee class for equality. So what I like to do is go to the models.scala file and add some equality logic to our employee class to make this work. So here we are in models.scala. And I have my employee class, and this is everything that we've worked up to at this point. And what I'd like to do is create an equals method, so that way we can make sure that equality between our Adas actually works. So let's get started. I'm going to start off with the override modifier. This is a keyword, as we stated in our previous session. Obviously def, this is a method, and equals. The method parameter for this will be any. And the return type will be Boolean. True or false? Does this object equal to the other object? This X right here will be the other object that we're comparing against. Now there are different ways to create implementations. I'm going to probably be a little bit verbose here. First, I'm going to ask the question, if X is not an instance of, we had talked about this method already as instance of. If this does not equal to employee, then we will return false. So we have to test whether X is of a type employee. If it isn't, we'll return false. Otherwise, we will cast it. And now other is of a type employee. Now we could ask questions like the following. Is the other first name that's coming in, is that equal to our first name? And this is a Boolean and. We're going to be testing three different things. And is the other last name equal to this last name? And is the other title equal to our title? This would be the last evaluated statement. This is one big statement, and this is a Boolean. Now, since we established this, we can then compare one object to another by calling the equals method. Again, this equal comes from the AnyRef. Let's run our script. First of all, let's compile models.scala, then run our script. Great. Take a look down here. Now, because Ada Lovelace's first name, last name, and title are all equal, we deem that these two objects are equal to one another. Now, there's something really cool about Scala. What it did is it took back the double equals operator. And if you're coming from Java, you might have a little bit of trouble breathing here. In fact, you are probably feeling a little bit confused. This means that everywhere that we used the equals, we can now use double equals, like the operator. So this is exciting. So let's go to our script and rewrite our equality checks. Okay, so right in here, we're calling the equals method. But we could forget all this and just state the following. We could also use not equals to as an operator. Let's run the script again to make sure that this works. Now, this should say true, and this one should say false. But what we're actually doing is we're actually using object equality, not reference equality here as it is in Java. This is going to be different. So I went ahead and saved this. Now let's run our script again. Great, we see right here true and false. But wait, we could also change our code in our employee class in our models.scala. So let's do that. Okay, so here we are inside of our models.scala, and we have all these equals. So why not change these up? We no longer need that equals, we no longer need this equals, and we no longer need that one. We could probably get rid of these outlying parentheses. That looks a lot cleaner. I'm going to save this. Let's recompile and run our script. Nice. I love you, Scala. That's really great. Now, how do we test if two objects are pointed to the same thing? First, let's take a look at this diagram and see what is meant by references. So we see from this diagram that these two objects are equal. We created a new eta and we created another eta. First name, last name are the same. The title is the same. So these are actually equals, but they're not pointing to the same thing. The reason is we called it with a new keyword. In other words, we instantiated separate objects and references are going to be pointing to two different objects. So how do we test for that? Well, let's go to our employee script and show you. So here we are, and what I'd like to do is show you how to test for equality. We're going to use a method called EQ. It's really an operator, not a method. This will test for reference equality. In Java, this used to be the double equals, but not anymore. This is now EQ. This is the way we test for references. These two are pointing actually to different objects, even though they are object equal to one another. This should also be false. These are pointing to two different objects. So let's go to our command line and let's go to run our script. There it is. There's false. Let's go back to our script, try something else. Now we have another eta here. If we just so happen to say even another eta is equal to another eta and ask if these two are pointing to one another, then this should be true because we asked even another eta to point to the same object as another eta. Let's save that and run the script. There we go. That is true. Now let's try out our hashCode. Hashcode is a generated number that is used to calculate where to store an object in things like hash maps and hash sets. Many object-oriented languages has this notion for a hashcode. Hashcode has to make every attempt to be as unique as possible and will need to return a 32-bit integer to identify that object. It's kind of like an employee number or social security number, some kind of number that identifies the object. I'll use Josh Bloch's recipe for hashcodes from his book, Effective Java, 2nd edition. So we move over to models.scala and add a hashcode. Okay, so we just got done with equals. So now let's create a hashcode. This is an override def hashcode. This will return an int. What we'll be doing, we'll be setting up a var here. And even though using a var can be a little bit dangerous, and over here it's going to be just fine. We're going to choose a constant non-zero value and assign this to a result. And what we're going to do is we're going to change the result. We're going to use a prime number, multiply it by the result, and add first name's hashcode to it. Take that same prime, and we'll add last name's hashcode to it. We'll take the title, multiplied by 31, and then finally return the result. Here's our hashcode. Now, once we return this number, it's no longer mutable. It was only mutable within the context of a method. And that's why the var in this case is okay. Not leaked outside. Nowhere outside this particular reference can this be changed. Now to test if we do have an efficient hashcode, let's test our objects to ensure that something that is equal has the same hashcode. This happens to be a part of the contract to test for equality and test for an effective hashcode. So let's go to our script. And the next thing what I'd like to do here is type out if new eta's hashcode is the same as another eta's hashcode. This should be true. And we could also test, let's use eta for example. Eta, remember, had a different last name. So this should also be true. That eta's hashcode, remember she has a different last name, the eta reference does, and another eta should have a different hashcode. So these two should not be equals. Let's save this, compile our models.scala, then run our script. So we have true and true. Let's go back to our code as the last two. True and true. The hash codes work. Now, because we have an effective hashcode, we can then use our employee objects in collections like hashMap and hashSet. So lastly, let's work up our toString. And as it stands right now, if we print out any employee object, we get some sort of messy output. Let's try it out first. So we're already here in our employee script. So let's add the following line. In fact, I'm going to do a print line new Ada toString, but we don't actually need the toString right here. So I'm just going to call new Ada. Why? The default implementation for print line is that it's always going to call toString regardless. I could be explicit about it by adding toString if I wanted to, but I really don't need to. So I'm going to go ahead and remove that. Now let's run our script to see the result. So we see employee at 5E1F756B, some sort of messy output. This shows the name of the class as well as an integer representation, really a hexadecimal type of representation of the object address. Not very helpful. So let's create a toString method for our employee. So let's go back to models.scala. We're going to do an override def toString, and we'll use string interpolation for this. You could do whatever you want here. Whatever kind of string you wish to represent your object, you can do so here. It is all up to you. Now let's compile models and let's run our script. Keep in mind, I didn't change anything with script, so what should appear is the actual representation that we defined. Now this is human readable. Employee Ada, Byron Countess of Lovelace, programmer. A nice string representation for our object. So equals tests for object equality, and we would need to override this equals method. But when we call it, we don't have to call it with equals. We can call it with the double equal operator. We can use EQ to test if two objects are pointed to the same object, or if they're sharing the same reference. Hashcode is a near unique, and I do say near unique. Sometimes collisions will happen, but you should try your best, and should return a near unique 32-bit integer that represents the object so that we can use it in things like hashMap and hashSet. And toString is a string representation of the object. And just an added note, equals toString and hashcode are all overridden from AnyRef. In this session, we discuss case classes. Up to this point, we've been pretty hard on you since we manually coded methods like copy, toString, hashcode, and equals. Case classes will do all of that for us. All we have to do is add the word case before the class keyword, and we can forget all about that equals, hashcode, toString mumbo jumbo, since all of that will be created for us automatically. I will say there will be some caveats to that though, but we'll discuss that at the end of the session. But first, let's try out our case class with department in our models.scala file. So let's head over there now. All right, so here is models.scala. And what I'm going to pick on is I'm going to pick on department, just because it's easier. We have department has one property, name. So let's go to our script, and we'll check to see that we indeed have a copy, toString, hashcode, and equals method. So here we are in the script. So what I'd like to do is give this a try. I'm going to create a toy department. First, let's try out toString, print line, toys. Now let's head over to our command line. Give this a try. So I'd like to compile models.scala first since we made a change to department. And now let's run our script. And as we see right here, here is department. So it indeed created for us a toString implementation automatically for us. Next, let's try equals. Let's go back to our code. So given this, I'm going to create another reference called toys2. This is a different object called department toys, same thing. And we would like to make sure that toys is equal to toys2. Let's save this and run it. That is true. Really good. So now let's try hashcode. Remember that checking two hashcodes of two equal objects should be equal themselves. So let's verify that. So toys.hashcode should equal to toys2.hashcode. Let's run that. So you see right here, that is true as well. Now let's try the copy method. The copy method is going to work the same way as our copy method did, the one we did manually earlier, a few sessions ago. So let's go back to our code and give that a try. So this time I'd like to create hardware, and we're going to take toys and make a copy of that. But in our copy, let's change the name to hardware. Let's go run our script. And there we go. Department hardware. So we have toString equals hashcode implementations. We have a copy method, case classes for the win. There are some other neat effects that case classes can give us. For one, we don't have to use the new keyword anymore to create an object. Let's go to our employee script and try that out. So this new keyword, get rid of it. This new keyword, get rid of it. Let's save it, and let's give it a try. Remember, this only works for case classes. If there isn't a case in front of it, this will not work. Script works just the same. Again, because we put a case in front of the class, the new is optional. One of the other neat things about case classes is that we don't need to declare vals in our primary constructor, since it's now assumed by default. So let's change the way our department looks by taking out the val for the name. And to do so, go to the models.scala. Again, we no longer need it if we're using a case class. So here we are under Models Scala, Case Class Department, and we have val right in here. Do we need it? No. So I'm going to get rid of it. Save it, and now let's check that everything still works. First, we compile models.scala since we made a change, and now we will run our script. Again, everything works as expected. Now, just so you know, if you don't like what is provided for you automatically, you could always override your own method while maintaining the other methods created automatically. So for this, let's say we want to create our own toString with department while keeping equals and hashCode and copy the same. So let's go back to our models. And what I'd like to do is override only toString, again, keeping the rest the same. So let's say that I don't like the way it looks by default. Let's go back to the command line just to show you how this displayed. So here's department toys and here's department hardware. That's what it looks like by default. States the class name, parens, and lists out all the properties for that one particular object. So what I'd like to do is just change the way this looks. Go back to our code. So I'd like for it to say now department, space, and then the name of the department. So I'll go ahead and save this. And let's go to the command line to see the effects of this. First, let's compile models.scala. Then let's run our script. Everything's the same from our previous run, except the way we do a toString. So all the equals, all the hashCode, everything else still stays the same. Now, case classes also gives us the ability to unapply code for pattern matching. Though pattern matching requires its own set of topics that unfortunately we don't cover in this video series. But let's take a quick example of what pattern matching looks like. Let's go to our employee script. Let's say we want to extract the name from one of these particular departments. I will choose toys for this example. And I wish to match on this. This is the way we do pattern matching. Pattern matching is very much like switch statements in other languages, except it's a little bit more robust. We can do a lot more with pattern matching. The way pattern matching works is we're going to put a case here. In this context, case means in case this is a department. And here I'm going to assign a variable. So whatever name is a part of this department, I'm going to assign this to n. And if it just so happens to match this type, I wish to return that n, that particular name. Secondary case, this underscore means what default means in other switch statements in other languages. This is pattern matching, not switch statements, but the underscore here is the default. And if it is not known, then we will return unknown. And then finally, I'll close out the brace. And in this case here, what I'd like to do is just print out the name. I get all this automatically by using a case class. So let me go ahead and save this. And let me go over to the command line and give this a try. Great, there it is, toys. In fact, since we have that, we probably did too much work. We could also simplify it very much like this. Let's go back to our script. Let's add a few lines here so that way it's not stuck down at the bottom. This is really interesting. What we're doing is we are extracting the name from toys, and name 2 is going to be assigned to the name of the department. So let's save that and let's give this a run. There it is again. Let's go back to our code. 1 line instead of 4. This is the power of pattern matching. Again, you get all this by using a case class. Now, a lot of these neat tricks are tucked away in a construct called an object, and we'll discuss that in the next few chapters. So now let's talk about the caveats I was referring to earlier. Although case classes are wonderful, they come at a cost. Here is that cost. Case classes cannot be subclassed by other case classes. One of the reasons happens to be one we encountered when we created our own copy method. We cannot inherit from a method with default parameters. The other reason is back a few years ago, when copy was being implemented, creating a copy method on a subclass returned an instance of the superclass. Of course, that was incorrect. That was really tough to implement at the time. So there is that limitation. Just be aware of this. Sometimes you want a case class, sometimes there's no way around that, and you're going to have to create your own toString equals hashCode and copy methods. As far as pattern matching, you can create your own on apply. As far as invoking or creating an instance without the new keyword, you could also do that manually, and we'll be discussing that in the next few chapters. But take heart, most Scala programmers will typically model a superclass as a regular class or abstract class, while the case classes will be the subtypes. And that you can do. So in conclusion, putting the case keyword in front of a class makes it a case class. Case classes have an automatic equals, hashCode, toString. You can instantiate a class with a new keyword. If you don't like the methods that are created, you could override your own. And you can have automatic pattern matching with case classes. In this session, we discuss abstract classes. Abstract classes are classes that have 0 or more abstract methods. What are abstract methods? Well, abstract methods are methods that must be implemented by one of its descendants, since there are no concrete implementations for abstract methods in the abstract class itself. Furthermore, abstract classes cannot be instantiated. So you cannot use a new keyword to create an abstract class. Since it is a part of the inheritance tree, any subclass of the abstract class can be assigned to that abstract type. Now that introduction had a little bit too many nerd words, so let's try an example in our models.scala file. Alright, so here we are in the models.scala file, and what I'd like to do is I'd like to do the following. I'm going to be right up here at the top, and I'm going to create an abstract class. So I'm going to go ahead and save this, and this is an abstract class. I have abstract in front of the class definition, and I have two methods. One's called first name that will return a string, and the other one's a last name that will return a string. Please note there are no implementations. I don't have equal something. Now let's do a quick sanity compile to ensure that we wrote this correctly. All right, that looks good. Now let's tie these all together, and let's have the employee type extend from person. So employee here will extend from person. Let's compile the code. Great. So why does this work? Let's go back to our code before we continue. Now remember, we saw in our video session in the section classes that if we put a val in front of a property, and we're talking about these vals right in here, it automatically generates a method called the same as our property. We called it our accessor method. In other words, the property first name has a method called first name because we put a val in front of that property. If we put a var, we'd have an accessor with the same name as well. Property last name has a method called last name, again because we put a val in front of that property. By that fact, it is reasonable to conclude that employee does adhere to the contract, that it or its subclasses must have an implementation of the methods first name and last name, and if we compile, we see that this is true. Not only that, we also see that from the compilation that also manager adheres to the contract as well, because manager extends from employee and employee extends from a person. Now, let's play with our employee script and do some polymorphism with this. So here we are back again. We've already established that in our own little world that Alan Turing is a manager, and that means that Alan Turing can be assigned to a manager reference, or it could be assigned to an employee reference, or now a person reference. So somewhere up on here, let's take a look back on here, we have a reference to Alan as a manager, and here it is. We have val, Alan, the type of this pointer is manager, and it is referring to a manager object. Since manager extends from employee and employee extends from person, what we can do is, let's give this a try down here, is that we can assign, let's say we want to create a reference called Alan person that only points to persons, and we wish to assign that to Alan. Will this work? Well, let's go ahead and save it and run our script. We didn't do any kind of print line, so just the fact that we're able to run it should be good enough. And it does. It works out just fine. Otherwise, we would have gotten an error. Let's go back to our code. Now, given new ADA, remember new ADA is this right up here. We're taking an ADA reference, copying it, changing the last name. Regardless of what happens, both ADA and new ADA are employee objects. So it stands to reason that we should be able to do the following. So we're taking an ADA reference, which happens to be an employee reference, and we're assigning it to ADA person, which is a pointer that points to person. Therefore, this is correct. This is just polymorphism. And again, though we have no output in this example, the fact that we are able to run it is proof that polymorphism does indeed work. We can assign employees and managers to a person reference. So we'll save it. Let's go ahead and run it. Everything works out fine. Let's go back to the code and review. So here it is. Abstract class has two methods. These are abstract, meaning there are no definitions. It is up to the subclasses to define these particular methods. But they are defined merely by the point of fact that they have vals. And because they are listed as vals, a method is developed automatically for us for first name and last name. So it adheres to this particular construct. So in conclusion, abstract classes cannot be instantiated. Abstract classes have 0 or more abstract methods. Abstract methods don't have the keyword abstract. They just have the implementations, and we're talking about the methods. The classes has the keyword abstract, but methods do not. You just don't create an implementation for it, and by that, it is already an abstract method. Since abstract classes are a part of the inheritance tree, very much like we had with person, employee, then manager, any object based off of that subtype can be assigned to that abstract type. In this session, we discussed parameterized types on classes. We've already discussed parameterized types on methods, but now we discuss what happens when we apply them to classes. First off, we know that parameterized types use square brackets. We've seen that with methods. Of course, the same holds true for classes. So to keep things simple, let's create a class called box in its own file, box.scala. So here's our editor. We have box.scala. We've already created the file. And I'm going to create a one-liner. Case class box. And here we'll have the parameterized type t. Meaning we could put anything we want in the primary constructor. We could put in an int, we could put in a string, we could put in an employee, we could put in a date time. So we'll finish here. Let's go and save that. This is a complete line of code. In the parameterized t states that the box can accept any type and that the Scala's type system will keep track of that type. So if we extract t at any point, we'll have the correct type. Now, the same rule as applied with parameterized types on methods, the parameterized type is always one letter, T, U, V, A, B, C, D. So let's create a script called box script that makes use of this box. And in here, let's create the following. I'm going to create one called int box, and this will be equal to a new box of 1. Therefore, T becomes an int. So what is the type going to be? A box of int. Let's try another one. This time, let's be explicit. What is the type? Well, it's already listed there explicitly, but this too is a box of int. Now, one thing, we don't have a new keyword. That has nothing to do with the parameterized type. That has to do with the box is a case class. Now, how about this one? Now, this one's using coercion. We're creating a box of 1. Although the type inferencer will already know what type this is, what we are coercing it, stating that this is a box of int, and do that before you assign it to int box3. So this too is a box of int. In fact, if I have int result of type int, if I call int box3 and get t, remember t is the property. Let's go back to our box over here. Here's that property. T is a parameterized type. So if we give it an int, t is now established as an int. So therefore, when we call t, remember this is also going to create a method. We could have had a val here, but we don't need to. It is a case class. Therefore, it's going to create a method called t. And this method called t is going to return an int if what was given to this box is a type of int. So let's go back. So therefore, when we call t, this is of a type int. So let's save this and let's run it on the command line. So first off, let's compile. Then let's run our script. Okay, everything ran just fine. We didn't have any print lines, but because it ran just fine, we know that our assumptions are correct. Let's go back to that script. Of course, we could easily use different types in our box. So let's try some. We can create a box of hello. We could do something like this to reinforce it, that what we want in here is a string of hello. Now for our next example, let's create a manager box. Again, with this box, we could put anything we want in it. And this will be a box of new manager. And let's try Kathy Sierra, who is a programmer and is with the Department of Programming, Learning, and Fun. So this one is going to be a box of string. This too will be a box of string. And the last one, although we have this on multiple lines, let's clean it up so it looks like this. This will be a box of manager. Let's run the script to make sure that our assumptions are correct. Works out great. If we wanted to, because manager is a subtype of employee, I could force it to make this a box of employee, where here the parameterized type is employee. That makes this box an employee. Let's run the script to make sure that works. Looks great. Now let's even get fancier. How about a box of double? Sure, let's go back. Let's call this one double box box, and this is going to be a box with 4.0. What is the type? This is a box of double. So let's say we want to fish out of here. So we have a box inside of a box. The box inside of the box has a value of 4.0. Let's say we want to fish out that 4.0. What do? Well, we take double box of box. We'll get T. Once we get T, this will be a box of double. And if we call T again, then we'll get 4.0. In fact, just to make sure that the types carry along with this, let's say we have a double result. This has to be a double. And we call double box box.t.t. And what we'll do here is instead call double result. And again, this is the reason for the parameterized types. We don't want to return an any or AnyRef. We want to return the actual type that is within this box of a box. In this case, that would be a double. So let's save this and run it. There it is, 4.0. Again, the parameterized type can be anything. And in this case, we have a type T. We could give it an int. We can give it a string, whatever it is we'd like. And the type system will track all of it. It's very important that all functional programming languages, and really all static type languages, keep track of these types, no matter how many layers deep it is. So how about classes with two type parameters? Sure, so let's create another file called couple.scala, and we'll create a class called couple, and this time with two parameterized types. Let's go back to our editor. So here we are at couple.scala, and a nice little one-liner once again, couple A and B, and we'll have one called first. This will use the type A, and again, type A could be whatever it is we want, and second will be of type B. Two parameterized types, whereas box only had one. So let's compile it. That looks great. Compiles, again, type A could be anything, B could be anything. And again, once established, type system will track those types. So let's create a script called couple script, and let's give it a script, and let's try a few different ones. Okay, this type is going to be a couple of int and string. This too will be a couple of int and string. And in fact, we could even make this explicit. Let's try another one. Okay, this is a couple of double and int. And this one is a couple of string and string. Now, let's try a complicated one. Couple of a string and couple of int and double. Interesting on that one. So let's say that this one is going to be a couple of hello, and this will have a couple of 3 and 22.2, for example. What is this type? This is a couple of string and couple of int and double. Okay, so as you see here, you can even place a couple inside of a couple. So given all this, let's go ahead and save it and run our script to make sure this works. That was the box script. What we need to run is the couple script. Works great. Now let's take apart one of these couples. Since it is a case class, we could do the following. Let's head back. So let's say the couple string, couple int double. We want to retrieve the 22.2. How do we do that? Well, what we'd like to do is we would like to get the second item and the second item from that. And this will return a double. Not only that, it's going to return a double with the type double, not any or AnyVal, double. Go ahead and save that, and let's run it. There it is, 22.2. Not only that, the 22.2 is of a type double. Let's go back to our code. So just to point out again that when we call couple string couple int double dot second, we're returning a couple of int and double. Once we call second again, we are returning double because of the type system. So parameterized types use square brackets. Parameterized types are managed by the type system. You can have as many parameterized types on a class as needed. Remember, they're all single letters and all capitalized by convention. A, B, C, D, U, V, W, etc. And as we saw with a couple of a couple or a box of a box, a parameterized type can contain other parameterized types. And the type system will keep track of all of that for you.